Good morning, everyone. Let's give your colleagues a few minutes to join. Hello, good morning, everyone.
Good morning, Henry.
Yeah, I'm doing well. How about you?
You're also doing very well.
We thank God. Okay. So let's begin. We always close on time, so let's begin a little on time. Okay. All right. So yesterday we talked about the fact that there are two types of factor analysis. Usually exploratory is used or is more appropriate when you do not usually when the measures have not been validated before. For instance, you pull from you selected or you sample from a pool of indicators. You may need to perform some EFA so that the software will group them for you before you go ahead to do confirmatory factor analysis. Sometimes you have gone for, you introduce a new construct or a relatively new construct that has not been measured before. So if you measure it in your study, then EFA becomes automatic. That become the baseline. You need to do it. In other studies, like replication studies, where you adopt the same kind of measures, sometimes EFA does not become necessary, but you need to do what we call the confirmatory factor analysis. So let's hope that you will have time to do both today before we end. So just to explain how the EFA works, okay, like you mentioned yesterday, EFA is based on correlation. So what it does is that you load all the items or the measures into the software, then the software perform a sort of correlation metrics, trying to see how each pair of them is correlated. Now, after that, it tries to rotate them around to group those that are highly correlated among themselves, just as you see in the second matrix. You see that it has brought V3, V8, V9, and V2 together because they are highly intercorrelated among themselves. You can see the correlation coefficients. Okay. For instance, if you pick V3 and V8, their correlation is 0.773. But according to the arrangement here, this is where V3 is. V3 is in this column, and then V8 is here. So it computes the raw correlations, inter-item correlations, then it tries to group them according to how their intercorrelation is, how large their intercorrelation is. So that is a grouping that has been done in this second matrix you see on the screen. So you realize that it is suggesting that the way V3, V8, V9, and V2 are highly intercorrelated, they must have one underlying factor or component that is causing them. And then the way V6, V7, and V4 are also highly intercorrelated, but their correlation with V3, V8, V9, V2 are smaller, relatively smaller. They are correlated, but it is smaller. You see, they are in the range of 4.4. But between V6, V7, and V4, the correlation is above 0.7, which means they are highly correlated. So this is what we are trying to explain yesterday, that these set of measures here, V3, V8, V9, V2, seem to belong to one particular construct. That is why they have a high, or their internal correlation is very high. It means that one phenomenon or one abstract notion is causing these things, these indicators to exist. The software doesn't read any meaning into the labels you have here. It only looks at the scoring of these measures and computes a correlation for them. So let's try and look at the face validity of these to see if we can even think of a plausible factor that could cause this. So I need your attention here. I will need your contribution. So let's look at this from V3 to V2. Return policy, in-store service, store atmosphere, store personnel. What concept or construct do you think will give rise to indicators like this? Return policy, in-store service, store atmosphere, store personnel. Can we guess? I just want to guess. What constructs will exhibit these kind of indicators? Applying the knowledge we had yesterday, defining a construct and making sure that there is the items you generate for the construct can be found in the definition. So even though here we have not displayed the name of the construct, looking at these indicators, what is it most likely to define? Return policy, in-store service, store atmosphere, and store personnel. Can anyone help?
Retail policy.
You said retail policy. Okay. That is about right because
shop.
yeah, okay.
Customer relation.
Exactly. It's related to those things. Okay. So that is good. So assuming you don't even know anything about this and you see the construct name and you see these indicators, you can tell if it is really truly reflecting the construct itself. And that's why we call the content validity, your ability to judge the meaning of the construct from the labels on all the indicators or the measures that have been used to measure it. Now let's try and guess for the second set, V6, V7, V4. Assortment depth, assortment with product availability. Can anyone suggest a construct or a variable that will exhibit these characteristics? Assortment depth, assortment with, and then product availability.
Product on sale.
Okay, product on sale. So technically, there are technical names for this if you are in marketing or in logistics, okay? So normally we term this service level. From my background as logistician, I look at this as service level, product availability, and it tells the extent to which you are able to offer a wide range of service to your customers. Since this has apparently it appears this has to do with a retail shop or something like that. So the number of products you have in terms of breadth and depth and width, and then product availability. Okay. Now, price, the last two is price level and then product quality. Price level and product quality. Can anyone guess a construct that will reflect these indicators? Price level and product quality. If you are buying a product and you are looking for high quality and also reasonable pricing, what comes to mind? Value. So those are, so let's see, okay. In-store experience, that was about right. Our guess was closer. Product offering, okay. Our guess was also closer here. And then value, we're just on point on that. So the software will just group them this for you and then label them component 1, component 2, component 3. But you know that this is in store from your literature review, your definition. You know that these set of measures, you were using them to measure in-store experience. And then these other 3, you were using them to measure product offerings. And these other 2, you are using them to measure value. Then you just put your the appropriate labels there. So that is it for EFA. We will do a demonstration with it and then okay. So in EFA and then even CFA, This is the structure we normally have at the back of our mind when we picture. Okay, your construct is here, and then its indicators are represented by rectangles. And we are assuming that it is because price consciousness, that is your construct, exists. That is why you see things like I shop for specials, I shop for bargains, I usually book for lowest price possible. Store brands are worth just as much as national brands. So these are the indicators, the measures of price consciousness. Now, if that is true, the loadings here shows the relationship between each of these measures and this. And it should be closer to 1, okay? So when you take the scale on your questionnaire, these will be scored against this scale. If I read this, I'll pick one of these. So you see that you are only supplying the software with just the numbers. And the software will try to build that correlation here and try to estimate the extent to which each of these measures relate to the one common factor, and we'll try to assign a regression weight, which we call loading, on the lengths or the on the arrows from the construct to the indicators. EFA will not draw the structure for you, but it will present the measures like this, and then present a columns that represent the factors. And if these set of measures belong to factor 1 or component 1, it will assign these loadings along that column, the space against each in that column. Then if the next set of measures belongs to column 2, that is component 2, it will print out the loadings corresponding to that column and then the measures as well. So we will try and look at how to do EFA in SPSS. But before we do that, I want to just take you through a few descriptives, just the essentials. I gave you a book, step by step, and a step-by-step process to SPSS by Julie Pallant. It will help you systematically to do any form of analysis. So you can learn, you can explore more using that book. Okay, but I'll just demonstrate a few descriptives to you. Then I'll do reliability test with some data, and then we'll do EFA with some data. The data will not be exactly as we have it in this tutorial, but just it will function the same way, okay? So let's go to, let me share my entire screen so that I can load the data and then demonstrate a few things for you to see. Okay. So I'll be sharing this data with you. Let me just put them, let me just share them with the class right away. Okay, so I have labeled one of them basic analysis descriptives. So I'll just use that one to demonstrate descriptive statistics for you. And then I have the second data labeled for reliability and validity analysis. So I'll use that one to demonstrate reliability and validity analysis for you. So this is the basic analysis data. Now I just want to take you through a few steps on the SPSS interface. When you open SPSS and you load it with data, it gives you two windows. One window is the data set Okay. And there is another window called the output window. Anytime you run analysis, it will display that in the output window. Now, when you come to the data set itself, it has two interfaces, two tabs. When you come to the bottom, we have variable view and then data view. Okay. So it is at the variable view that you design your data set to receive your data. When you have collected your questionnaire, just like I showed you a sample questionnaire like this. Okay. I have my descriptives at the bottom. So you see something like, please indicate below the full-time number of employees in your company. Then the person will write, how many years has your company operated in Ghana? And then which of the following best describes your company in terms of the kind of activities you engage in? Which of the following best describes? So basically, this is the descriptive information I'm taking about the companies that responded to this questionnaire. I just want to put it side by side to show you, to explain to you what happens in preparing for you to enter your data into SPSS. You need to have variables, create variables that match the questions you have on your questionnaire. It is an appropriate practice to always give an ID to your questionnaire, the questionnaire that you have received. You need to create an ID for them so that you can distinguish each entry from the other. So when you have collected your questionnaires, you just number them, give them a unique ID. And usually we use the counting numbers from 1 to, if you have 20 questionnaires, then definitely your ID will range from 1 to 20. Okay. So and when you are creating variables in SPSS, you give the variable a name. The name should not contain spaces. Okay, and it should it's a good practice to keep your variable name very short, usually not more than 8 characters. That is so because you will have the chance to type out the full details of the variable. The variable name is just a short way of identifying the variable, and it has a label. At the label, that is where you provide the full details about the variable. So you write the name of the variable, and then you indicate the type of variable it is. So it can be, the types of variable can be so many, but the common ones we use is the numeric and then string. String is when you type out the name like male, female. If that is how you are entering the data in words, then you use string, okay? Then you have so many other ones here, date, dollar, custom currency, whatever. So you need to specify the type of variable. So in our case, most of our entries are numeric, quantitative, because we are dealing with quantitative data. So the default is always numeric. I'll leave the width and decimals for you to just figure out. These are very easy. And what is important is the label. That is where you have the chance to describe the variable fully. So we put here R gender, it's a respondent gender. ID, questionnaire ID. Edu, then we put the full meaning here, educational level. Weight, respondent weight. RA, religious affiliation. So I guess you get the picture now. Now, the next important thing is values. The scores you make for your variables, you will be entering for your variables. What do they represent? For instance, if you pick gender, respondent gender, when you see a score of 1 for gender, what do you mean by 1? When you see a score of 2 for gender, what do you mean by that? This is where you specify it. We are dealing with quantitative data so that our values or our scores are numeric. but those numbers have meaning to us as social scientists. So what is it? And this is where you specify that. So in this particular data entry, we said if you see a score of 1 for any respondent, it means male. And if you see a score of 2, it means female. So this is where you specify the meaning or the value placed on each of the numeric entries you make for your variable. So for educational level, let's see. 1 is for non-formal education, no formal education. 1 is up to senior high. 3 will mean up to tertiary education. Okay. So you see that age we did not, because age we just enter the respondent's age, so we do not have to assign values. Okay. But you can also create age groups and all that. So this variable is age group. It was derived from the raw ages here. So let's see. If you see under the age groups, if you see an age group 1, it means from 20 to 30 years. Age group 2 means 31 to 40 years. So I guess you get the picture also here. Now, the next important thing to specify when you are designing your data set is to indicate the measure, the level of measurement. So just as we discussed about data structure, a variable must have a name. A variable has a scoring, which is the value. And we have indicated that here. And a variable has a measure. So we need to indicate the level of measurement we have for each of our variables. For ID, 1 doesn't make any difference from 2. It's only showing that 1 means questionnaire from respondent 1, and 2 means questionnaire from respondent 2. So it is nominal. Because the categories are more than 2, it's nominal. It's not, we won't say it's binary, it's nominal. But SPSS doesn't go into those nitty-gritties. It considers all categorical variables as nominal, whether it is binary, that is 2 grouping, or more than 2 groupings, it calls them nominal. Male and female. Male is male, female is female. It doesn't make any difference. One is not bigger than the other. We are not trying to look at it from that sense. So that one too is nominal. Even though it is binary, it is still under the nominal scheme. Now, educational level. Non-formal education, and no formal education is lower than those who have attained SHS certificate, and SHS certificate is also lower than those who have attained a degree. So you see that there is some kind of order here. We can arrange them in order of magnitude. So that becomes ordinal. The SPSS only use 3 differentiation: nominal, ordinal, and then scale. And you see the scale, the label, it looks like a ruler. So just by the icons around them, you can easily identify them, even if you don't know the meaning of the name like nominal, ordinal, or scale. Now let's look at the raw age. We are entering just the raw age. So an appropriate way to capture that is scale. Weight in either kilograms or whatever. That one too is entered just as it is. So you can take any figure, any form with even decimal points and all that. So that one too takes a scale. Christian religious affiliation. This is religious affiliation. Let me close this questionnaire. I think we are done with it. So religious affiliation, Christian, Muslim, and others. You being a Christian doesn't make you better than a Muslim or any other religion. It's just classification. We are just classifying you based on your religious affiliation. So that one too is nominal. So I guess you get the picture. So what you do is every statement that respondents have to respond to in your questionnaire, you have to repeat all those as variables. Make sure you select the type of variable it is, numeric, string, date, or whatever. Make sure you indicate the labels so that you can make reference to the variables. Make sure you indicate their values if that is necessary, and then as well as their level of measure. This is very important because SPSS will have to, how SPSS will choose to treat each variable will also depend on the measure you assign to it. Okay, so it's important. So assuming we have created this for our data entry, then you switch to data view. And this is where you actually pick each questionnaire and you enter the data per each questionnaire. So the rows you see here, row 1, row 2, row 3, all the way down up to the end, we have 62. It means our sample size is 62. Each row represents a case. So this is questionnaire case 1, has a questionnaire ID of 1. The gender is 1, which is male. Education is 3, which means they have up to tertiary education. Age is 45. Weight is 65. Religious affiliation is 2, which is Muslim. And then on and on and on and on. So that is how you, so when you pick the first questionnaire, you enter in the first row, so that the variables are appearing on as the labels for the columns. So this is the basic data structure. Your variables appear in columns like this, and your cases appear in rows like this. Case 1, case 2, case 3, case 4, up to the 62nd case. Now, these are the values. The entries you make for each variable against each case is what we call the value. So case 1's ID is 1. Case 1's gender is 1, which means male. Case 1's education is 3. Okay, so the entries you see here is what we call the values. One we learned from our previous discussion last week. Okay. So once you have entered your data like this, the next is to explore the data using descriptive statistics. Okay. So to begin with the descriptives, the analysis you do in SPSS, all the tools are under the analyze. We have data. If you want to do anything about the data, sort the data, transpose, and hello, Francis. Francis.
Yeah, Henry.
Yeah.
With the data capture. Yeah, can you hear me?
Yes, I can hear you. Mm-hmm.
Okay, so with the data capture, you are saying we enter the data into the SPSS data view. What if
Yes.
you have data of over 100,000? Do you enter them, or you can still copy? How do
Oh, you
you
mean
copy?
if the data exists in different forms,
Yeah,
like in Excel or even in text and all that? Yes.
well, yeah.
Yes, you can import different file formats into SPSS. I don't want us to go so much into that because that's why I give you the manual. If not, we won't be able to do the what is necessary. Okay. You can import data. So you go to file and then you can import data. So if you go to import, there are different, you can do that even from a database. You can do that from Excel. You can do that from CSV. It is similar to Excel. Text data, SAS, Stata, and a whole lot. Okay, you can do that if you have them or if you have the data already entered, especially when you have used a platform like the online platforms to collect data, Google Forms and all that. You can download the data sets in either Excel or Google Sheets. And if it's in Google Sheets, it means you can open in Excel. So you can always import. Some software will even allow you to import directly from um, Google Forms directly. Okay. So all that exists, but I would want to leave that one for you to explore because the most important thing we want to demonstrate here is the measurement model evaluation. That is more technical. These how to set up the data sets and enter the data is something basic you can learn from the manual I give. Okay. It's not worth spending so much time on these basics. So, or if you just pick any video from YouTube to learn how to set up the data set for entering data in SPSS. In just less than 10 minutes, you can get adequate knowledge on that. Okay. All right. So this, I try to look at this because this interface looks just like Excel. Once you have created, in Excel, you just come here and type ID, type the variable names on top like this, without going through what we did from the variable view. But you see that if you do that in the variable view, you are able to add a lot of details that you cannot get in Excel. So if you import Excel data here, you will have to come and do these other ones manually. Okay. So let's go back to data view. So once you just set up the variable view and you come to data view, everything else looks like Excel now. You just pick your question and you enter. If you have the data, secondary data already existent, then you can import. You can think about importing. Okay. All right. So to begin with any form of analysis, you come to the menu and you pick Analyze. And these are the families or the various groups of statistical analysis you can perform with SPSS. So there are plenty: reports, descriptive statistics, tables is something we'll be using. Comparing means is something you might be interested in. And correlation is here. Regression is here. Log linear regression. Classification, okay? And then factor analysis is also here under dimension reduction, and then scale. So if you follow with what we are doing, you'll be doing something in descriptives, tables, you'll be doing something in correlation regression, and then you'll be doing something in dimension reduction, that is factor analysis, and then also scale reliability. These are what we'll be using just to cover a few things in this course. So let's go to descriptives. Usually, SPSS use the label or the function descriptives to provide a basic summary about your variables. Once you pick any analysis form, it tries to pull all the variables you have in your data set on one hand, so that you select the ones you really want to perform analysis on and then push them to the right hand. Then you can set some settings, you can adjust some settings about it, and then it will produce for you. Now, the descriptive we have here is usually appropriate for scale variables. So you see, it puts your variable and it tells you the type of variable it is, the measure of that variable, so that you don't forget. Descriptives here means SPSS is going to produce the number of valid cases. It will tell you the minimum, the maximum, the standard deviation, and the mean, the skewness, and kurtosis. So let me just go to option here and you see. These are the things descriptive analysis will produce for you. So you should be aware and you ask yourself, the variable I'm choosing here to perform descriptive analysis on, is it something we can compute the mean for? Is it something the software can compute standard deviation, maximum, minimum, variance, range, and skewness and kurtosis for? Just as I described, yes, I explained yesterday for you. When it comes to the central tendencies, mean is used for scale variables. And then when it comes to categorical variables, we use things like mode, frequency, and stuff like that. So if you know your statistics right, that's your statistics theory right, you know that if you choose descriptives, this is what is going to be produced by SPSS. So you ask yourself, which kind of variables can I place here to perform this kind of analysis? If you just put anything there, SPSS will try, but it won't make any sense. So for just to demonstrate, I'll select educational and then gender, and then add the right type of variables and then put here just to demonstrate for you. And then we go to options. Yes, we want the mean, standard deviation, minimum, maximum, That is fine. Let's add ketosis. This helps us to have an idea about the distribution of our variables, each of the variables. Okay, so continue. Style, what style? It just asks for how you want the table to be printed. Okay, the default is always adequate. So we have selected our variables, we have pushed them to the right hand side, meaning that we are telling the software only perform this descriptive analysis on these set of variables we have selected. And we have gone to our option to select what we want the software to do for us. And then you just click on OK. It will print the results in the output window. Hello.
Henry, do they have the software?
That I can't tell, because we could have done that if we had met in person. And
But they say they want to meet online.
Yes. So that is a disadvantage. You'll have to get the software themselves, and then
they have to get it themselves
and practice.
But do you have that book on?
Yes, I've shared it with them.
Okay,
step by step. Yeah, manual. SPSS survival manual. Yes, I've shared it.
Then they should be fine.
Yes. Yes.
Okay.
All right. So
we have let me trial version for now.
Okay, trial version for a few days. Let me clear my output. I had done some initial analysis, so I'm just going to repeat what I did. Analyze descriptives so that, okay, so I've selected my variables, I've put them here, I've indicated the options. So, okay, so now we have a clean output. So this is the table SPSS presents you with the descriptive statistics. So it tells you the number, the count, in terms of how many entries were made for each of the variables. So right from here, you can check if there is any missing variables. You know your sample size, so valid is 62. Now, against each of the variables, if you see a number here that's less than your sample size, then that tells you that probably there is a missing score, a missing value for that variable. So you now go to look for which case that has a missing value for respondent gender. So as we see here, all our variables obtain full entries, so there is no missing value. Now we have the minimum and the maximum entry for each of the variables we have. Gender, we know the minimum entry has to be 1. So if we saw anything other than 1 here, it will tell us that then there is an anomaly in the entry for gender. So we now have to go and look through our data to find where we made an entry which is bigger than the minimum, okay? And then we have the maximum, or even lower than the minimum we were expecting. Now we also have the maximum. According to how we plan to make our entries, the maximum entry we can ever make for, or score we can ever assign to gender is 2. We know 1 is male, and then 2 is female. So if you had any score greater than 2, that would be an indication that there was a wrong or a typo or a problem with the entry you made for the variable gender. So you now have to go back and go through to see where that problem is, and then you can fix it. So you do the same cross-checking for all the other variables to make sure that you are within 120 and minimum of 54. We are talking about weight, so that makes sense in kg. And then age, 22, and then the maximum is 79. That makes sense, unless 79 is too huge and to be is too high for any member of that class or any member of your sample. Then you want to go and look out for this person. Either you remove them because they are an outlier in your study, or if it's a typo, then you cross-check from the corresponding case, I mean the questionnaire to type in the right thing. You do all these checks because whilst you are entering the data by hand, you can easily make a mistake. Sometimes you want to use the tab to move to the next, it doesn't go, and you enter a double number. So descriptive analysis just helps you to quickly take a quick look at your data to see if there are problems in your data. So mean tells us the average score for each of the variables from your sample, okay? So it gives you an idea what the central tendency of each of your variable is according to the distribution of the variable, the data points in that variable. So gender, it says 1.48, but you know, computing a mean for gender doesn't make sense over here. Okay, there is no mean for gender. Because it's categorical, the appropriate way is to use a central tendency would be the mode. That is the most occurring gender. So it doesn't make sense to compute mean for categorical variables. But like I said, I just wanted to demonstrate this for you so that you will appreciate why it doesn't make sense to do that. Educational level, the average says 2.06. This statistic in itself doesn't make sense, although we know you are trying to determine the most popular level of education among your sample. But again, because it's a nominal variable, you would prefer to use count, frequency, okay? And then if you want the most occurring, you will use mode. That is the highest frequency, the response that the response that has the highest frequency for educational level. Okay. But for the scale variables like age, continuous variables like age and weight, their mean makes sense. It tells you that the average age for our sample is 44.19, okay? And the average weight is 79.65. And they make sense in themselves. All right. So standard deviation tells us how the extent of variability in each of the variables. That is when you look at the distribution of the scores on each of the variables, how closer are they or how widely spread they are, okay? So it checks variability. If it is too big, it is not good for you because it may suggest that the sample may not belong to one population. And if it is too small, that variability will not help you because, you know, we are doing estimation here. So if the variability in the data set is too small or too close, what it means is that the variables do not vary enough to allow you to identify any useful pattern in the data set. So you want it to be reasonable, not too huge, not too small. All right. Now, skewness and kurtosis helps us have an idea about the distribution of each of the variables, the distribution of each of the variables. So let me pull back this drawing we're making the other time. So though it's not perfect, we are using this to represent the normal distribution, how the curve is. And we were explaining last time that for parametric analysis, you want your variables to have a distribution that is closer to the normal school bell shape, according to the normal distribution theory. So this distribution we have can take different form. When it is like this, flatter like this, the mean is in the middle and the rest of the data points are scattered on the left and on the right. We taking the central, which is the mean. What it means is that some of the data points will be lower than the mean on the left, and some of the data points will be larger than the mean that is on the right. Now, the peakiness of the distribution. So just follow the kind of transformation I'm making to this. how peaked it is or how flat it is, okay, is described by the statistic or the measure kurtosis. Now let's come to skewness. For skewness, I have to draw, I have to pick another tool and then try to demonstrate that for you. So, and then let me duplicate this. Flip. Okay. So for skewness, let me do something here. I'm coming. Just a minute. Just give me a minute. Let me try to do this. All right. Okay. Okay. So let's assume this is a normal a distribution that follows the normal distribution theory. So we have the mean in the middle here. The mean always occurs here. And you can see that the rest of the data points for this assumed variable are sort of equally spread around the mean on the left and on the right, such that this line in the middle representing where the mean, the central tendency of this distribution appears, it looks symmetrical. It looks like a mirror. What you see here is what is repeated here. It tells you that the variables, the data points in that variable are well spread around the mean, okay? So this is the normal distribution we expect to have for each of the variables. So, but when you come to skewness, it sometimes happens that the data points are skewed either to the right or to the left. This is what happens. Here, the mean, on the right-hand side of the mean, only few data points are there. And on the left-hand side, only few data points are there. On the right-hand side, there's plenty data points scattered over there. So it tells you that the chunk of the data points are smaller values. That is where there's an influencing entry, which is an extremely small value that is influencing the mean, so that it is happening here on the low side. Whereas there are extreme values spread around on the high side. So we normally say when the distribution is like this, it deviates from the normal distribution that's kind of symmetric on both the right-hand side of the mean and the left-hand side of the mean. But when you come here, the data is skewed such that the entries on the right-hand side of the mean, and the left-hand side of the mean are not symmetric. So if you make any statistical analysis based on the mean, it will not be representative of the sample you are using. And it can also be skewed to the left such that the mean is towards the positive side, whereas there are plenty entries or data points that are on the left-hand side, just like this. So when this also happens, you have failed to achieve symmetry in your distribution, because the shape on the right-hand side is not similar to the shape on the left-hand side. So if you use this mean to make any statistical analysis using the parametric approach, the estimate will be biased. It cannot be trusted. Okay. So an example is what I mentioned to you yesterday, that if in a class you expect the average age among the 10 students in a class to be like from age 10 to 15, and you find that after collecting data, you find that there is one person in that class that is like 95 years. If you compute the mean will be very large towards the right, positive. Meanwhile, there are plenty of data sets on the left, which is lower than the mean. So if the average, if the age is supposed to range from age 10 to age 15 in that class, and you have somebody in that class bearing age 90, and you compute the mean for that class, definitely the mean is going to be extremely high, but on the right side of the mean, only few data points will be there. And in this scenario, only one person will bear the, will have a high score, whereas the rest of the data points are on the left. So you don't want this to happen. You don't want the distribution of your variables to deviate from the normal distribution assumption, which looks like a school bell. And the ketosis has to do with the extent to which this is flatter or so peaked. If it is too peaked, what it means is that there is little variability in your data points, such that they are not too different from the mean. And mostly, if you have this situation, then your standard deviation will be very small, It means all the data points you have are so close to the mean that in statistic sense, you will say then they are virtually the same. They are not different from each other. So you can't actually identify any pattern, useful pattern from your data set in terms of exploring relationships. So when it is too peaked like this, then we say it has a positive ketosis. Then when it's too flat too, we don't want that. We don't want it to be too flat. If it is too flat, what it means is that the other data points are further scattered away from the mean. Okay, there is too much variability in your data set. And when there is too much variability too, it tends to suggest that your data doesn't seem to come from a common population. And that also affects the estimates you make from your analysis. So we want, at the end of the day, we want our distribution to look like the normal school bell. That is not too peaked, and that is not too flat, and which is symmetrical. The data points are perfectly represented on the equally represented on the left side of the mean and also on the right side of the mean. Okay, so those two evaluation is what we see in the output here, skewness and ketosis, and they have their statistics. And the rule of thumb we normally use around here is that you don't want this statistic to be either more than 3. The absolute value is 3. It can be positive or negative, but we don't want it to be more than 3. So for our scale variables here, I think we are within spec, such that a perfect skewness statistic would be like 0. So the center would be like 0. If it's perfectly symmetric, it will be 0. If the ketosis is also perfect, that is the peakiness of the distribution curve. If it is perfect, it will be 0. That is why we are saying the rule of thumb is either plus or minus 3. If it's within that range, we accept. But we are not in a perfect world, so you might not get 0 for the distribution of your variables, but they should be within plus or minus 3. Okay, so once you your descriptive analysis produces skewness and ketosis scores for you like this, you can have a fair judgment whether your variable deviates significantly or not from the normal distribution assumption. So this is it for descriptive statistics. But for a very useful, when you have a mix of categorical and scale variables like this, continuous variable like this, instead of using the descriptive option in the analysis to perform a table like this, which is not appropriate representation for your categorical variable, you can also use this function in SPSS called tables. Table allows you to bring different things together and assign different properties to them, different variables types together, and then assign different properties to them. So we will use tables to also demonstrate, and you see, demonstrate how to do a comprehensive table that includes both categorical and nominal and then continuous variables. Now, anytime you want to use that custom tables, SPSS will demand that you confirm if you have defined the variable properties, that is their measure, their level of measurement. If you have not indicated that, SPSS will not be able to will not allow you to use this function. But we have done that in our data sets already, so we can go ahead. So it gives you a chance to build a table. So you will select the variables just as we did before, just the same variables. Now, when you have selected them together, you click and hold and drag, and then make sure your cursor turns into a finger like this on the horizontal bar, which will be giving us the rows. So it just creates a table like this for you. By default, SPSS identifies that the first two are, one is nominal, and then the other is ordinal. So it picks the levels in each variable. Respondent's gender is male, female, education level, no formal, up to senior high, up to tertiary. But then I realized it recognizes that the last two are continuous variables, and it assigns a mean to them. But for the categorical variables, it assigns a count, that is frequency for them. If we had not indicated their level of measurement, SPSS wouldn't be able to identify them like this. Now, maybe you need more than mean for these continuous variables. You need the minimum, maximum, and then standard deviation, and maybe skewness and kurtosis. You can add that. Count, you may want more than just the frequency. You want percentage. It to also compute them in terms of percentage, not just the counting. Okay, so we can add all that. And this is how we do it. The variables that are count variables are respondents, gender, and then education. What you do is you press down the control button on your keyboard, and then you use the cursor to select the two of them like this. And then you come to define, and then you select summary statistics. So these are the characteristics or additions you can add, or layers you can add to your table corresponding to your count variables. So we may want to add, apart from counting, giving us a frequency, we may want to indicate the percentage, the column percentage. So you just expand here, column percent, and then you select column n percent. And then you can use this arrow to move it here. So this is what it will display for our nominal or count variables. Once you are done adding whatever you want to add, there are plenty you can add, but this is what is necessary for us. So you click on apply to selection. Once you click on it, believe it has done it, then close. So you see that it has applied a new column, which is the percentage, to only the count variables. Okay. Now let's assume for the scale or continuous variables, you want more than, excuse me, I mistakenly picked that out. Okay. You want more than just the mean. So the same thing, you hold on control and select the two of them, and then summary statistics. And then you look out for what you want to add apart from the mean. Okay. Let's say we want to add the minimum, we want to add the maximum, we want to add the standard deviation. Okay. All right. So we've added this, and you can actually arrange them. Maybe if you want the minimum to come first, and then maximum go second, you have mean and standard deviation. So you can use these other arrows to move, to arrange how you want it to appear. If you are done, you apply to selection, and then close that window. And it adds minimum, maximum, mean, standard deviation for your continuous variables. So once you've actually arranged or formatted your table to your satisfaction like this, then you can click on OK, and then SPSS will produce the table you have specified for you. So for most of the things we do in our thesis, you would use custom tables a lot. It's a one-stop point where you can have all sort of descriptive variables you have in your data set and produce just one table to accommodate all of them, including count variables and then continuous variables. So we have 32 males, 30 females, and it presents them in percentage. That means we have 51.6% of the sample or respondents being male, and then the remaining 48.4% being female, which makes sense than going to use mean. Okay, using the mean to summarize the count variable gender. And also educational level, we know we have, for those who have no formal education, there are 18 of them, constituting 29% of the sample. And then senior high education, 22, and then up to tertiary, 22, okay? And of course, your continuous variables, we have the basic descriptives for it, minimum, maximum, mean, 16. A table you can easily present at the preliminary stage of your data analysis in your chapters, your chapter 4, your data analysis chapter. All right, so this will just be for the demonstration. You can use the manual to learn other descriptive statistics. So we want to go and learn how to do reliability test using Chromback Alpha. So for the rest of the demonstration, we use the other data. Hello, are you speaking to us? Okay. So kindly mute yourself. All right. So let me leave this window. So for the measurements analysis of reliability analysis and then validation, we'll be using these data sets I labeled for reliability and validity analysis. Okay. So yesterday we looked at reliability analysis as trying to measure the extent to which a set of measures capturing a construct, the extent to which they have internal consistency. Okay. So we have these variables in this data. Green procurement, we have all the way 1 up to 10 of them. No, is it green procurement? Let me see. Helping suppliers to implement green. Yeah, all right. So green purchasing practice or procurement practices. I don't have the constructs of head. It's been a long time we work with this, but what we see here is that these constitute measures for one construct, and then from PRD1 all the way to 7 also constitute the measures for another construct. And then we have GEO1 up to 5 also constituting the measures for another construct. And then we have SPP1 up to 6 constituting the measures of another set of constructs. So when it comes to the multiple item constructs, this is how we construct their variable names in SPSS. You use the same sort of variable name, but you distinguish it with numbering so that if you have 6 measures for it, you'll have SPP1, SPP2, all the way to SPP6. So you can tell that GEO that contract has 5 measures or 5 indicators. So they are labeled GEO1 all the way up to 6. So that is how you are able to tell the set of measures that are being used to measure one particular construct from the other when you look at the variable view. Okay. So let's begin from here where I can easily tell green entrepreneurial orientation. And then this is overall cost reduction, products, innovation. I'm just trying to look at the labels to see if you can find the name for it. Shorter new product launch. Okay. Product differentiation, innovation. Then shorter customer order fulfillment time. So it has to do with some sort of performance. Okay. It has to do with some sort of performance. So let's assume our study is looking at these 2 constructs. Okay. What we do in reliability analysis is select only the measures of the construct we want to check internal consistency, that is reliability on, and then perform the generate an alpha score for that set of measures. Achu?
Yeah,
Let's hear you.
Yeah. So please, I want to find out the values column is none. Do we have values there already? Why is it none? Not defined.
Okay. Yeah, okay, that's a good question. So this is a scale, what do you call a Likert scale for each of these measures. Okay. So they range from 1 to 7. So you can actually enter the labels for them, depending on how you label them for your questionnaire. Maybe very poor. 1 could be very poor. 2 is, let's say, poor. 3 could be, let's say, neutral or something, all the way up to the highest.
Yeah,
But
right, but I tell you, those things they don't change anything.
Yeah.
They don't change anything. So the thing is that you are going to give command to the program to do analysis for you. So you should know your data before coming to the analysis. It really changes nothing really in terms of the output you get.
Yes,
because they are continuous variables. You understand?
Exactly.
They're continuous variables. So what matters is the numbers, not necessarily what you are typing in it. But it becomes important when it's a categorical variable like age, like gender, sorry.
Mm-hmm.
Because the output will now generate results that is consistent with what you have entered. So if you say 1 is female, and if you say 0 is female, 1 is male, the output will show that. That's if you are dealing with categorical variable. But if it's continuous variable,
it doesn't matter.
They don't really matter.
Okay, so please a follow up. So I'm just curious. Assuming this variable, let's say we compute sort of average or mean on it.
Mm-hmm.
How would you locate that if the scale is not really important?
But you have that on your questionnaire, right? You as the designer of the study, you have that, right? You know that. You know what 1 means. What we are saying is we entering it here is not relevant. It doesn't mean, because these are measures that we only want to take them through purification and transform them to make our actual analysis. So at this stage, it is irrelevant to put those labels there. I don't know if you understand us.
Yeah, I got it now. Thank you.
Exactly. Because these are continuous variables you are going to manipulate, you are going to compute averages and stuff like that and use them for something else. So at this stage, it is not necessary to enter those ones. So, but what is important is what Prof said initially, when you have categorical and ordinary.
So in other words, this is what we call raw data.
Raw data.
This is the raw data. You are going to create new variables out of the raw data for purpose of further analysis. Right?
All right.
Chief, do you understand that?
Yes, please.
Okay, so can we continue? So I will do the reliability test demonstration for just these two constructs. That is green entrepreneurial orientation, and then this is a form of performance. Okay, it's just another construct. It has 6 indicators. So you'll have, for reliability, you have to do it for each set separately. Okay. So let's go to analyze, and you come to scale. Then you pick the first one, reliability analysis. Okay, it falls under this heading. So you have your variables on the left. Now you see that because we have the labels of our variables here, it is displaying the labels instead of the variable names. We can change this by right-clicking on any of them and say display variable names, which should be easier for us to identify our variables of interest. So for the construct GEO, it has 5 indicators. You select all of them and push them to the right. Now let's look at our options here in statistics. So it can provide descriptives for all the items and the scales if you want. It will do that for you. But what this test does by default is produce the Cronbach alpha score for you, which yesterday we saw how to evaluate it. A good score is 0.7 and above, and below that is a poor score. So it will do that by default for you. But for you to be able to diagnose whether there are issues with any of the items, we normally include this option, scale if item deleted. We are trying to purify these measures or these items we have put here. So we want to see, should we drop any of them? Will it improve the alpha score or not? It helps you identify critical measures or items that contribute to capturing that construct. So that is just it. And then you click on OK. Let's go for output. I think it's one of the analysis that gives you a very simple output. It gives you a case processing, how many valid cases there are 128, and the total in terms of sample size is also 128. So everything was included. There was no missing value. Now, this is a table you are interested in at first glance. Cronbach alpha, 0.470. Number of items, 5. So from what we learned from yesterday, would you say this set of measures, would you say they pass reliability test or not? Our alpha is 0.470. Does it pass? Does this set of 5 measures, do they pass internal consistency? What will be your judgment? Hello? What will be your judgment? Of course, it's less than 0.7, so it doesn't pass. We want this Cronbach alpha to be at least 0.7. And then approaching 1. The score, alpha score, is computed from 0 to 1, the maximum being 1. 1 means perfect consistency. So anything approaching 1 is good from 0.7 upwards. So we have 0.4 here tells us that that is bad. Now, if you have a bad alpha like this, then it becomes necessary to evaluate this other table, that is item total statistics, to see if you can identify the culprit from this table. Now, what you are interested in is the last column. That was what we specified, that it should check item total analysis if a particular item is removed from our analysis. So already we have 0.47 here. We want it to go up. Now, this is what it does. This table says if we delete the first measure, this is what our alpha is going to be based on the remaining 4. If we remove the first alpha, the first measure, our alpha score will reduce from 0.47 to 0.38, which we don't want. We want to improve our alpha score. Alternatively, if we remove the second measure or item, it is going to reduce our alpha from 0.47 to 0.367, which is also not a good thing. All that is telling us item 1 and item 2 are all relevant, such that if we remove them, the internal consistency drops. Now, item 3 also does the same thing. It reduces our alpha. Item 4 reduces our alpha. But item 5, if we drop item 5, alpha improves to 0.9, which is very high. It improves from 0.4 to 0.9, almost very close to 1. So it tells us that there is a problem with this, our 5th measure or our 5th item. Now, why it is problematic, we don't know. But all we know is that if we drop it, our Cronbach alpha will improve for the remaining 4. That's why we call this a purification process, because we try to identify problematic indicators, and we try to resolve the reason why they are problematic. And if we cannot resolve it, we drop it so that we can focus on the remaining 4, which seem to be internally consistent in capturing green entrepreneurial orientation. So we now know that among the 5 measures, measure 5 or item 5 seems to be problematic. So let's go back to our data set and try to scrutinize this particular variable to see if we can find the problem. So we go to our data set, we go to data view, we navigate to GEO5, and this is GEO5. Okay, so sometimes it could be the fact that let me just reverse this. No, there's no ID here, so I can't. Let me just come back. It could be that there is a typo in your entries. So we have already sorted this out. I wish we had not done that earlier so that you see the raw things. You expect your values to be from 1 up to 7. The maximum should be 7 and the minimum should be like 1. That is the Likert scale you use. But look at here for the first case. You see that the entry for GEO5 is 90, way ahead. And let me tell you, if we had done descriptives on this, we would have discovered this. The minimum would be 1 and the maximum would be 90. That alert would have come through the descriptive analysis. But remember, we did the descriptive only for the other data sets, so we didn't do here. So that's why the descriptive analysis is very important. Once you do, you begin to even identify culprits before you begin your analysis. So this is the reason why item 5 is problematic, because there's an unusually high score here, 90. Imagine the range is supposed to be 1 to 7, and there is a single entry of 90 for one of our cases under GEO5. So if you identify an anomaly like this, what you need to do is to go back to the questionnaire corresponding to that case and try to see the actual score that was supposed to be put there, and then you correct it. Sometimes it is not that there's a problem with the measurement itself, but whilst you were entering, you made a mistake and you put an unusually high value there. That can cause the problem we saw. So, assuming we correct this, and assuming by going back to the questionnaire, the value was supposed to be 5, and we put 5 there. If we repeat the analysis, we should expect a better result. If we don't, and we have gone through all and we have not seen any unusual entry in this measurement, then we have to drop that measurement for GEO. Okay, so let me repeat the analysis again. Having made the correction here, it was 90. We realized it was 90 and we realized, no, this one is unusual. Maybe it was a typo. So we go back to the questionnaire and we find that the right entry is supposed to be 5. So we put the 5 there and we come back to repeat our reliability analysis. So the same 5 measures have been put there. Okay. Wow. Now let's see. Reliability has increased to 0.926. Let's check item Chromback Alpha if item deleted. Now, look at what we are seeing. If we remove item 1, it will improve Chromback Alpha from 9.2 to 9.3. But already 0.9 is huge enough. So we wouldn't want to be greedy by dropping more, losing more information just to improve alpha from 0.92 to 0.93. There isn't much difference. Other than that, if any of the other items are deleted, alpha score will rather reduce. Okay, so it tells you that we have been able to fix our issue without necessarily dropping any of our measurements. Okay, so sometimes it's just the fact that you made a wrong entry that is causing the alpha to be smaller, or that measurement item itself is not similar with the others, so you may have to just drop it. Okay, so you need to understand why a particular measurement is causing your alpha score. Then if you find out the reason and it's something you can fix, you fix it. If there is nothing you can do about it, then you drop that measure so that you can have the remainder giving you a good alpha score. So let's repeat reliability analysis for the performance variable. So we are doing it for the next set. So we remove them from the right-hand side and come SPP1 all the way to SPP6 and shift them here. I'll maintain the same settings and then okay. Okay, so with this, we have an alpha score of 0.808, which is within our the expected recommended range. Okay, it's well above 0.7. Now let's see if dropping any of the items or measures will improve. Only item 4, shorter new product launch time. If you remove it, it will improve it from 0.8 to 0.81, which again is not, the difference isn't that much. Already our alpha is good, so we are not hungry to increase our alpha. And even the increment we receive is not too big that we will need to drop this item. It is better to retain much information than to drop it for just a trivial improvement in our alpha score. So these set of measures also demonstrate high internal consistency, that is high reliability. All right. So that is it for demonstrating reliability analysis. We perform it for each set of measures for the constructs in your study. And the rule of thumb is that you want your alpha score to be approaching 1. So an alpha score of 0.7 and above is recommended. Any question? If not, I'll move on to demonstrate to you. All right, Francis.
Yeah, I've been trying to follow what you are doing. I'm trying to do the same here, but then when I go to check for my reliability, I don't see the names GP1 and 2 as you see in yours. I see the full description, so I'm unable to pick.
Okay, so like this, you don't see this, you see
Yes.
the labels. So
Yes.
I said initially when I did, this is what I saw, and I said you just right click on any of them. Okay, right click on any of them and you select display variable names.
Oh, okay. All right. Thank you.
Okay. And sometimes when we are even done with our descriptive analysis where we need the labels, we sometimes remove the labels so that we are only left with just this, so that it becomes easier to work with. Okay, so that is it. So to report this, you make a table of all your constructs, and then you create a column for the number of items you use in measuring each of them. And then lastly, you put the alpha scores for each of the constructs, and then you report it. All right. Yeah.
Within your
other people have their mics on. Can you put them off? Yeah.
Yeah, sorry.
You have multiple.
Within,
Yeah.
yeah, within your reliability analysis, you said we should add the skills deleted. But when we analyze, we were only using the comeback. What is the skill variety deleted?
Okay, so this is the reliability statistics produced in Chromback Alpha. This is this small table, okay? And this is the alpha if item deleted table, okay? If you followed from the first example, that would be this, okay? Our alpha was small. This table, that option you checked, it produces this additional table that helps you diagnose why the alpha is small, okay?
Oh, okay.
And we found that if we, so what that means is it iteratively deletes each of the items, the measures, one after the other to see if the remainder will produce a better alpha. So it deletes the first one, this one, the first measure, and it tells you the alpha that will be given if it is computed based on the remaining 4, which is not also good. Then it comes to delete the second one, and then it computes alpha based on 1, 3, 4, 5, and it tells you the alpha, which is also not good. It comes again to delete item 3, and it calculates alpha based on the remaining 4, and it gives you the alpha. Then it continues to do that to the last item. Then we realize that when it deletes the last item and computes alpha based on 1 to 4, the alpha becomes significantly high, 0.9, giving us that, telling us that item 5 has a problem. And when we went to check, we realized that item 5 has an entry of 90 in one of the cases, which is unusual. Okay, so the data I shared with you, if you run alpha for GEO 1 to 5, you are going to get 0.4. But then we went to inspect why that, and we discovered that there's an unusual entry which was 90 for one of the cases under item 5. And then we assumed, we went back to the questionnaire for that case, and we identified that the entry was supposed to be 5 and we entered 90. So when we corrected it, now we got a repeated analysis, we got a better alpha score. Okay, so that table helps you diagnose which is a problematic item in your set of measures. Is that understood?
Okay, thank you.
All right. So you just need to, at the end of the day, if you have 5 constructs, you compute alpha score for each of those constructs. You pick the set of measures and you compute alpha. Then when you finish, you now have to pick the alpha scores you got for each of them, and then you put it in a nice table, a simple table that have in the rows the constructs you are trying to measure, and then in one column how many items you use in measuring each of them, just as is reported here in the small table. And then in the last column, you present Chromback's alpha, which is the corresponding alpha score you obtain for each of those constructs. And explaining that table is simple. If the minimum among the alphas is greater than 0.7, then it means all your set of measures demonstrate high internal consistency, which is reliability analysis, and that is it. Okay. We won't have time to report this in or in Office Word for you to see, but just to give you the idea. When you pick any thesis from the library, you will see how they present the tables, and then you can do same. Those ones are office skills. All right, so let's try and demonstrate EFE, exploratory factor analysis, which is a way of establishing initial validity. Okay, so this is for reliability analysis. So we are going to validity analysis using EFA. Okay, so let me go back to the data. So we are using the same data at this level. So let me go to variable view. Again, we want to focus on the measures for GEO. For this time, let me add one more variable, two more, so that you have a sort of like many indicators to work with here. So we'll be working with GEO1 all the way to SMP4, and it contains 4 constructs. The first being this GEO up to 5, and the second being this, and the third up to MD1, that is market dynamism, and then this is market performance from SMP1 to 4. Okay, so to do that, let's go to analyze and then come to dimension reduction. Okay, dimension reduction. Then we select factor. So I'll just change these into variable names. Okay, so we will now go and select all the indicators we are interested in from GU1 all the way to SMP4, and then we put them on the right-hand side. So let's go to the options for descriptives. So here you specify some of the descriptive analysis you want the software to generate as part of the solution. By default, it will give you an initial solution. And if you want universal descriptives, you can add, but it's not relevant. I think we just check those that are important for what we'll be doing. At the end of the day, you want to know if your variables, the data you have supplied, okay, is able to, there is enough correlation among them to undergo factor analysis. And remember we said EFA uses correlation approach to group your measures into factors. So to test whether your data passes or is adequate enough to be able to generate that kind of metrics, we select for the software to generate some descriptives for us here to help us make a judgment whether our data is sufficient in terms of their correlation to generate output for factor analysis or the EFA. So you select significance level and then KMO and Barrett's test of sphericity. All right. So usually these statistics or these formulas were designed by human beings who put their names or their labels on it. So just for you to know what is irrelevant here. That's all. Now I need to determine the extraction method. By default, we use the principal component for what we are doing, but there are other ones, alpha factoring, image factoring for other purposes other than what we normally do in social science studies. So for us, the principal component is what we will need here. Now, how you determine the number of factors that will be extracted, the optimal number of factors that, or the relevant factors that will be extracted. It gives us, it can display a graph called a script plot that helps you visually determine the number of significant factors or relevant factors from your data set. So you can check that one. And then it uses another approach to generate the number or to evaluate the number of significant factors that can be extracted from your data set. And it uses a computation it calls the eigenvalue. You wouldn't want to go into the details about this. What it simply does is it tries to iteratively compute different number of factors from 1 up to the maximum. So if here we have how many indicators here? 5 plus 6, 11 plus 4, that would be 15, plus another 4, that would be 19. It tries to assume that each of these indicators can be a factor on its own. So by default, it will generate 19 factors. Now, so the last number of factors will be 19. It will begin by generating 1 factor, and then it will generate 2 factors, 3 factors, all the way up to the maximum number, which is 19 factors. We, from our theoretical perspective, know that we are expecting about 4 factors, but the software doesn't know that. You have only given it measures, and it's assuming each of them can even be a factor on its own. So the worst solution to give you is 19 number of factors. Now, for each number of factors it extracts, it does that based on the correlations it computes. And then if it's, for the number of factors it extracts, it computes what we call the eigenvalue, which is a representation of
Hey, Michael, you be hosting.
hello.
Sorry.
All right, so I'm using cellular, so you can continue. All right. So by default, any factor that has an eigenvalue of 1 is deemed a significant factor. Okay. So it tries to put some sort of a what the eigenvalue computation, which I don't understand the mathematics behind it, but what it seeks to do is it tries to assign some level of significance to that factor. The extent to which that factor contributes to the variances in the entire data set. Okay, so the extent to which it contributes to explaining the variance structure of the entire data set. Okay, it tries to assign a score to each of the factors it extracts. So by default, it says that any factor that obtains an eigenscore of 1 is deemed a significant or a relevant factor for you to consider in your data set. So we will leave it at that default and click on continue. Now, remember what we saw from let me just bring that out. Before the laboratory practice, we saw this table and we said this is what EFA does. It computes just the correlation, the item correlation, and it will try to bring together those items that seem to have a strong correlation together, just as we saw here. Now, it does that behind the scene, but it doesn't rotate them to group them like this for you if you don't specify. Okay, so you need to specify a method of rotation. So by default, it does now. It won't rotate them for you. It will just do the thing and then present you with a messy table, which doesn't organize them. But when you specify the rotation method, it will rotate them nicely and then organize them for you to be able to make much sense from the matrix it will produce for you. Okay. And for our type of construct we are looking at, which is reflective constructs, we normally go for the option very max. These other options are used for other type of constructs, depending on how they are, the conception about how the construct behaves is. We won't have the time to go into those details for now, but for the usual things we do, we normally take the variance rotation. Then you say continue. For now, let's take it. Let's take to what we have the modification we've done here. You repeat it again and then show what options we can check from here, so that the information is not too much for us. So once you've indicated this, made your specification in these first three tabs here, you can just click on OK. And then your output will be provided. So it gives us our descriptive statistics and as results on the correlation metrics from our data. So measure of sampling adequacy. And again, these are from 0 to 1. So we want something closer to 1. So anything 0.7 and above is a good measure of sampling adequacy. Okay. And then its significance is also it computes the Bartlett test of sphericity as we specified. We specified it to produce two measures for us, the KMO and then also the Bartlett test of sphericity, which also check whether there is adequate correlation in your among your variables to warrant or to extract significant factors from them. And it produces a chi-square measure of which we are looking at this. The significance to tell whether our measures have adequate correlation among them that allows us to come out with distinct factors or components from the data set we have supplied it. And you want this to be significant, okay? You want this to be significant so that we know we are able to extract distinct factors from it. So once we have good sampling adequacy, say that the sample we have provided is enough to undergo the factor rotation, which is we evaluate by looking at this value to be at least 0.7. And then the fact that there is adequate correlation in our variables to extract meaningful components or factors from it is also significant. So we are good to go. So the next thing, we are not interested in the correlation matrix, but we want to determine how many factors have been extracted. So this is the table reporting the eigenvalues for us, which we said by default, if a component has the components have more than or an eigenvalue of at least 1, it is considered a significant Sorry, thank you. So this is the eigenvalues computed for all the components that have been extracted all the way up to 19. So if we are using the rule that only items that have an eigenvalue of 1 or more should be considered a significant component to be extracted, then you see that we have 4 components. That is component 1, 2, 3, and then 4. We have only 4 significant components. Now, from this table, we want to see how these components contribute to the total variance in our data. So it computes the percentage they contribute in representing the structure of our data. Component 1 contributes around 33%, and component 2 alone contributes 14%, and component 3 contributes 11%, and component 4 contributes like 6.7% to explaining the variance that exists in our data structure. In the third column, it does it in cumulative. So first one produces 33. If we add the second component, our extraction, that is if you extract only 2 components, 1 and 2, it accounts for 47%. And then if you add the third one, it accounts for 59. And if you add the fourth one, it accounts for 66. What we want is that our factor extraction should account for a majority of the variance in our data set. So at least you should, the number of factors or components you decide on as relevant factors or components to be extracted should be able to together account for at least 50% of the variance in the data supplied. Okay, so given that per our rule of thumb, our 4 components explain more than that 50%, which is 66.4, it means the number of significant components to extract account for a good percentage of the variance in our data. So from here, theoretically, and also from what the software provided, analyzed for us, we can see that extracting 4 components is optimal for our study. Now, graphically, you can picture that from here. So you normally say that this graph, called a scree plot, starting from the largest number of factors from the right-hand side and moving towards the left, where it takes its first sharp bend, we call it the elbow joints, tells us the number of factors that that is optimal to extract. When you locate the first sharp turn, then you look at the number of factors or components on your your left-hand side, and that becomes the optimal number of components to extract. Okay, so if you observe this, it is gradually climbing up, but it takes a sharp bend from here onwards. So on that point, when you trace down, some will look at it from here. If you look at it from here, from 5, moving from 5 to 4, that is where the sharp bend occurs. The first sharp bend, the rest were just gentle bend of the curve. But it begins from when you move away from 5 to 4. Okay, so it is not at 5, but when we're moving from 5 to 4 component, that is where the bend came. So it tells us that 4 components will be optimal to extract from this, our data set. So it tries to generate, based on the rule of thumb we set in this table, that it should extract components with at least an eigenvalue of 1 to draw or to generate this component matrix for you. But as you see it, these are not rotated, but it gives an idea the members of each of the components. So when you take component 1, its members take the first, second, third, fourth, and fifth measures. Yeah, I'm using it. Whereas it is difficult, this table is not well organized in terms of how the, hello, Ransford.
Please, it's time for break.
Oh, okay. Like I told you, I'm a talkative, so thanks for reminding me. So, okay, 2 minutes. So we return at 10:30, right?
10:32.
10:35.
Make sure you are online exactly 10:35 so that we can continue our discussion. Thank you.
You're welcome.
Welcome.
Yeah, Ransford.
Is Prof online? Prof.
Let me see.
Yeah.
Okay, Prof, good morning.
Honey.
Please, about the assignment. He said we should do it in groups, and please, I want to find out the groups. Are we supposed to create it ourselves, or
Yeah,
you
you create it yourself. You haven't done
And-
it yet.
no,
Oh, create the group of 4 or 5.
4 minimum.
Or 5. In an exceptional case, it says, but ideally it should be 4 or 5 people.
Okay, that's fine. All right, sure. I wanted that clarification. Okay, thank you.
Okay.
Henry.
Oh,
We were talking
sorry.
about
Yeah, I was muted. Okay.
Before you go
So-
back to what you were saying, I wanted to ask, when
Okay.
we were doing the settings for the rotation for the factor, within the new version, they have this Kaiser normalization. Does it affect anything? Because I realized within your values, you were getting 0 zeros, but within my, I was getting less than 0.001. Does that make any difference anyway?
Come again. You said
When you were doing the settings for the rotation factor.
rotation.
Yes.
Okay, let me just go back to that window. No. Dimension reduction factor. Here.
Rotation. Yes.
Mm-hmm.
Yes. The new version that we downloaded, that the trial version, it has this option of Kaiser normalization.
It's here. It's here. Is it not here?
Not that one. The rotation
Really?
has this. Yes.
Then I've not seen that before.
Oh, okay. I thought it because it was checked, and my values were a little bit different from yours, especially
From here.
0.00.
So check in the chat. I've sent you links to download SPSS and then Amos.
Oh,
Okay.
This was
So
Amos.
my version is, I think the one I've sent you is 26 or, let me see. It should be 25 or 26. And then the Amos version is 23. So you can pick the links from the chat and then download them later on. Okay.
Please, what is the AMOS for? Is it also similar to SPSS or it's an add-on?
It's not an add-on, but once you install it, it is also integrated into SPSS. But when you are working with it, it opens a separate window. It is used for the CFA. It can be used for the CFA. There are several softwares for that. But SPSS has it's called the same platform, structural equation modeling, and IBM's own is the EMOS. Okay.
Okay. Thank you.
All right. Okay. So we are back looking at our rotated component matrix. And this is the table you usually report in your study. So what it does is it takes the, if you pick component 1, you are looking for the measures that have high loadings on or correlations with component 1. And just as we've been talking about that same rule, any of the measures from the scores that are calibrated from 0 to 1, the closer it is to 1, the better. So you want loadings that are quite high. Ideally, you want loadings like 0.7 and above, but a loading of 0.5 and above indicates that that measurement item loads significantly on that particular component than others. So if you pick a measurement item 1 like this, you can see that it loads on what? Component 1, 0.716, whereas on component 2, just something small, component 3, it loads on it 0.32, and then component 4, only 0.1. So even though it has some kind of correlation with all the other components, you can see that its parent component would be component 1. Now, when you look at the remaining ones, you can see that component 1, 2, 3, 4, 5 all seem to load on component 1, meaning that this component you have here, its name should reflect this. And we already know that, and that is GEO. Okay. So the software is not able to make any sense from the labels you have here, neither the variable names. It only made sense from the scoring from the entries. And it was able to deduce that these set of measures seem to have one underlying component. So that is why it is called exploratory. The software is just exploring blindly with just the scores from your questionnaire. We did not specify to the software that these constitute one factor, or these are supposed to be indicators of one component or one construct. But the software, based on the entries, the correlations, how they are correlated among themselves, found that they are likely to be indicators of one parent component. And he has just labeled them the first component. And then when you look at, so when you cross-check down to, you should expect that all the remaining measures should not load significantly on that component. Okay. So when you have a case where other components or other indicators are loading significantly on the component they are not supposed to, then it tells you that there is a problem of cross-loading. A component, a measurement item doesn't know where it belongs. It seems to be confused. It is loading on other components that is not supposed to, theoretically, it's not supposed to. It gives an indication that that measurement item might also be a problem. And you consider whether removing it by first reviewing its content validity, examining if by removing it, it will not distort the meaning of the construct, and 2, by checking the data itself pertaining to the data pertaining to that variable to see if there are no anomalies, just like we saw in the example in the what do you call it? Alpha reliability computation. Okay, so let's see for component 2, the measures that load significantly on component 2. It begins from here. Overall cost, product innovation, product differentiation, But I see shorter new product launch time, but at least it is above 0.5, so we can tell it still belongs to component 2. Shorter customer order, component 2, and then flexible products and order fulfillment system, component 2. So you can see that these are the set of, from here, these are the set of measures that load on component 2. It tells you that the software has been able to recognize them as indicators of a common component or factor. And we know that these measures are measured as SPP, okay? So we know that. Now, component 3, when we scroll down, we see that the high loadings are occurring for the 1, 2, 3, 4, the 4 remaining, the last 4 indicators. And of course, by looking at these indicators, we know that they belong to market performance, as we had in our data set. So these 4 also belong to one construct, which we know the name, okay? And then we have significant loadings here, 0.7, 0.7, 0.7, 0.7. There are 4 of them, which also correspond to these measures. And these loadings are on component 4. And of course, we know market dynamism. These are the measures, indicators for market dynamism. So we know that component 4, we will change the label of component 4 to market dynamism. So in the rotated matrix, component matrix table, you are able to tell how the software classifies our components, our measures that we supplied it into components based on the correlation between the each of the items and the extracted component. And what we are looking for is that for their corresponding components, the indicators should have loadings of high loadings, okay, of 0.7 and above, ideally. And then while at the same time, if an item loads on a particular component, it shouldn't load significantly on any other component. So you look out for the fact that an item loads on component 1, it shouldn't load significantly on any other component. And if you look at component 1, if these are a set of measures that loads well on it, when you scroll down, the remaining loadings shouldn't be that high on it, okay? Now, this table can be reported the way it is, but the matrix has values in every box. Sometimes it can be difficult for the eye to clearly map out which component the a set of measures are really loading onto. So that what we do is you just bolding the significant loadings. So these set of significant loadings, we change them to bold font. We come here, we select all these and change them to bold font. That is when you are taking the table into your Office Word and you are formatting the table, you can do that. Alternatively, you can go back through the process and come to this course, come to options, where you can instruct the software to show or suppress coefficients that are less that are within certain range. So we can say that it should suppress small coefficients that are below the absolute value of 5. When you do that, it cleans the table more for you and then show you only the significant loadings. So let's see the same thing, rotated component matrix, and this is it. It becomes more clean and you only see the significant loadings for each of the components. You don't see the cross loadings. Okay. So in most cases, this is the table you will see, or it will be just like the old one, the former one, like this, but they will change the significant loadings into bold font so that they can easily be made and be compared to the non-significant loadings. All right. So when the software is able to extract components like this and assign the measures to them, and you look at the output and it reflects exactly what your theoretical, your measurement model you had in mind when you developed your measurement model or your questionnaire, then we say that it provides an initial, it demonstrates validity. Okay, each set of measures converges in measuring or capturing a single component. So these first 5 sets converges in measuring or capturing one component, which we know that that component is green entrepreneurial orientation. And we see that the correlation of the measures here to the other components were not significant. Okay, so that also gives us an initial evidence of divergent, discriminant validity. If you look at these other sets, their correlations are high for their corresponding component, which is component 2, which we know is SPP. But when you look at A's correlation with all the other components, they were all tiny. That one is more clear when you look at the other rotated metrics that we have not cleaned out. So this is what I was saying. These are the loadings. They are stronger on component 1, but when you compare their cross loadings with other components, they are not strong. So it gives us an evidence of convergent validity. These measures come together to measure one component, whereas their correlation with other components are tiny or smaller. So it gives us an initial evidence of both convergent validity and discriminant validity. So normally you report this table and the descriptives about it and how you arrive at the decision of extracting 4 components from the data from the total variance explained, which we did earlier on. Okay. So based on extracting the components based on those that have an eigenvalue of at least 1, and then ensuring that their total variance explained should be more than at least half of the variance in the data. So the 4 components accounting for 66.4% of total variance shows that it is optimal to settle on the 4 extracted components. Yes, actually.
Yeah, so I want to ask, when you were cleaning, you gave 0.5 as the parameter. I want to find out, is there any decision rule with regards to how factors are supposed to load or something?
Yes, that is, I have mentioned that severally. Ideally, you want the loadings to be, you see, it's calculated from 0 to 1. And the more you approach 1, the stronger the loadings. So the rule of thumb is, it should, like, ideally you want 0.7 and above. Okay. Think of it this way. The whole from 0 to 1, the maximum is 1. So if it belongs to a particular component, it should load at least more than 0.5 on that component. But then you see that some of the it will spread its loadings, the remainder of the correlation was spread across the other components. So you want that each parent component, it should load very high, and then to the other components that are not the parent component, even if it will load on it, it should be smaller. Okay. We don't want to go by the strict 0.6 because you are still at the initial stage of measurement purification. 0.7. If we were to go by 0.7, it will eliminate most of the indicators, but this is not the final stage of measurement purification. Okay. If you have gone for that, this item will be dropped, this other item will be dropped, and this will be dropped. Okay. But remember, we said we want to retain as much information as possible. So when something is too terrible, then we remove from it. But at least this still shows that it loads more than half of the variance, that is 0.5, on this component 2. Chances are that if we apply more stringent measures, it will take this item out. This item is actually problematic because when we did reliability, we saw that if we remove it, it improves reliability. Okay. So we can go and investigate from the entries to be sure that there is no anomaly in the entries. And then maybe we can go ahead to drop it from our analysis. So this is just the initial stage I'm showing, so that once we go through them and identify problematic measures, then we can, or indicators, we can drop them and see how it improves our validity. Okay, you wanted to say something else?
Oh, I understand perfectly what the explanation you give.
Okay.
I wanted to even ask that how terrible can it be for you to drop it, but you said it's the initial stages yet, so.
Yes.
Maybe.
So remember, yesterday we were saying, we were trying to address the question, how many measures should you include in capturing a constant? And we said, not too many and not too small because of this exercise. Okay. So from the reliability, we could have dropped the 5th item for the GEO if upon going to the data set and there was no a typo in it, then it will just mean that that measurement item is bad for us, so we drop it. So here in this case, assuming we have gone to check and there's no anomaly in the entries for this particular measurement item, then we will say it's not a strong measure for this construct. Already we have 6, so we can afford to drop some and have some to spare. You get it? You don't just drop items or measures anyhow, but it should be based on their significance, okay?
Okay, thank you.
So, assuming we don't want to go and do even a more stringent, apply a more stringent, that's the next level, CFA. And maybe we just want to end at EFA here. EFA gives an initial indication, the weaker, what do you call it? Indicators or measures here. So, assuming we don't even want to go further, since we have plenty measures to spare here, we can decide to drop this particular measure, which is shorter new product launch time. We can drop it and then we can just see how it improves the whole term. Surprisingly, what will surprise you is that these loadings, okay, the loadings you see here can be affected by the fact that this is not part of this particular, this is not a good indicator for this component. So if you drop it, sometimes you even come to see that all the other indicators have even improved in their loadings. That's how interesting it can be. All right. So under that assumption, I think it is the most, it is one of the indicators that's loading very poorly, even though it has indicated that a strong association is with component 2. It's loading quite poorly. So let's remove it and see how the component matrix will improve. So we repeat the analysis. And over here, because we have the labels in our data set, it will print the labels instead of the variable names in the output. But we can trace it. It is 1, 2, 3, 4. The 4th under SPP. And this is it, the 4th under SPP. So we can take it out. So we now have SPP 1, 2, 3, 5, and 6. 4 has been removed. Let me continue. So we come to our rotated component matrix. And at least there has been some improvement. There were 2 of them which had 0.6, but now only one has 0.6. This is what I'm talking about. We have 0.6 for the 5th item and 0.69 for the 4th, the 2nd item. but that has changed slightly by removing the poorly loading item. So at least this is something we can work with. So if you run this to one decimal place, you see that all of them will be 777 here. This will be 7, okay, and this will go 8. So that is it for now. Any other question here for EFE? Okay. So I would want to use Amos to demonstrate to you how we can do CFA. Yesterday we were looking at the 2 types of factor analysis. This is why we just did EFA. We can go and do CFA. And I want to use Amos to demonstrate that for you. There are several softwares like Lizra you can use. It will be more easier if we were in person to use Lizra for me. But we will just use SPSS Amos to demonstrate CFA for you. And we said with CFA, you propose or you come out with the measurement model structure. And by structure, I'm referring to this structure. You will tell the software that these set of measures are intended to measure to capture this latent construct, and these sets are intended to capture this latent construct. And then the software will superimpose this model on the data you have supplied it, the covariance metric structure of the data you have supplied it to see the degree of it. In EFA, we didn't have to specify these relationships. We just supplied it with the software with only these measures, and it decided to classify them into components based on their commonalities, all right? Based on correlations. So that is what we'll be doing in CFA. CFA, we will try and draw this structure and ask the software to determine the degree of fit between this structure that we have drawn and the covariance metric structure of the data points, the scoring the respondents did. Okay. So if you have Amos installed, automatically it shows in SPSS under the analysis, the last item, it will show IBM SPSS Amos. Okay. So for me, I can just pick the Amos interface from my SPSS interface. But then it will load IBM SPSS Amos for you. And then it will, this is something I did with some previous class, so I'll just clean that up. Just start a new thing. All right. So this is what you get, is a blank interface, and you need to prepare your new project to be for you to work on. So just to start, I will save the project I'm going to create. I've started a new project. I just have to save it. So just anywhere you can remember. So let me put it in my downloads, create a new folder, practice. And then I'll call it CFA. CFA data analytics. Okay, so CFA. So just any name you can identify with. So, all right. To begin with, in Amos, you need to set the interface properties. This is the interface that you are going to be working with. It's just like a sheet or a page that you are going to work with. So you come to view interface properties. So it's like a paper, a working space you are going to be working with. So you can determine the size. By default, it gives you the portrait and a letter size working space. You can change all that to landscape, whatever you want. Landscape A4 or the same portrait, but then A4. Okay. Any size. It just increases or changes the shape of the page you are working with. So it's calibrated either in inches or centimeters. So you can do that on your own. Font, formats, color, everything. You can explore them and then you can change them to suit your preference. So I will just go for what we have here already. Again, there is analysis properties. You use this interface to specify some properties concerning the analysis you are going to be making. The estimation method is the first tab, and by default, it uses the maximum likelihood estimation, which is the default for almost all the structural equation based platforms or softwares. So you can, depending on the kind of analysis you are doing, you can change the estimator. But for CFA, we use maximum likelihood, the maximum likelihood estimator. All right.
Hey, I'm logging out. I'm joining, start another class.
Okay, correct. Thank you.
All right.
So there are some other options on the left here. You can estimate means and intercepts, okay? That is the basic descriptive of means and intercepts for your model. And you will see here, EMU Lisrel 6. Lisrel is another SEM platform that is used for structural equation modeling and CFA, widely used. So sometimes if you are using a different platform, you want to emulate this legendary software. So you may want to check that. All right, now when you come to the bottom here, it says for the purpose of computing fit measures with incomplete data, fit the saturated and independent model. That is usually the default and we stick with that, okay? You don't do much there. All right, numerical. What we are interested in here is the iteration limits. What statistical software does when it is solving a problem for you is it puts the problem into several iterations to arrive at a solution, okay? And the default number here is 0.5, 50. So it will use by default 50 iterations to try to solve your problem. What it means is that it tries to solve the problem going through its algorithm of solving the problem. It doesn't usually solve the problem in the first step. It may have to do it a number of times before it can really solve the problem to achieve an optimal solution. Yeah, like if you give somebody a problem to solve, they may make several attempts before they can finally solve the problem. That is what this one does. So by default, it gives 50. If you think your problem is more complex, then you may want to increase this, but 50 is usually adequate. Now, the criteria for determining significance level are also shown here. Okay, this is 0.5 and this is 0.001, 0.05 and this is 0.001. So they are just the criteria for determining convergence or significance in running. And usually we leave this for the default. So we don't normally change anything here. Bias. We normally do not change anything here. You just want to be sure that you are, for the covariance supplied as input, you are using unbiased covariance. That is the raw covariance structure matrix, okay? And then, but for the covariance to be analyzed, we use the maximum likelihood estimator. And these are the defaults, and we stick to them like that. Output. When you have run your analysis, what do you want to see? It tells you the minimization history. That is a summary of the iterations that were done, and then before the results were arrived at. Standardized estimates. This shows us the standardized loadings, similar to the loadings in EFE. We want that. It will not automatically check all those things for you, but in the output, you have to specify. Squared multiple correlations. At this stage, we don't need squared multiple correlations, but if you want them, you can check them. Sample moments. It tries to generate basic descriptives for all your samples. So you may want to, we don't need them in CFA, but you may want to generate them just to have an idea. And then implied moments, residual moments, modification indices. Modification is important. All these are optional, okay? They are not so important what we are doing, but I'm just adding them, okay? But something like modification indices is very important to help you further purify your measures in EFE. It helps you diagnose a CFE. It helps you diagnose problematic indicators and how you can deal with them, okay? So whilst you are doing CFA, you would want modification indices. It suggests certain modifications that can improve your model for you, your model fit. Okay, factor score with, yes, covariance of estimates if you want to see the covariance structure. Remember we said EFA uses correlation and then CFA uses covariance. They are two different things. And correlation estimate, if you want to see them, fine. For me, critical ratio is important. It tells us the significance of each of the loadings. EFA doesn't give us the significance. It only shows us the magnitude, whether it is closer to 1 or not. But CFA helps us to determine the significance of each of the loadings. So you can take that one. And then in Amos 2, you can also check for the normality and outliers directly as part of the output. So if you are interested, you can also check it. All right. So I think you've selected enough here, and then that should be okay. You can go through the remainder of the tabs later on to learn from them, but for what we are doing, this is just adequate. So we have set our space to work, and we have made settings on the outputs we want when we are analyzing our data. Okay. Now, the next thing is you have to make sure your data is, the correct data is loaded onto Amos. If you have opened your data like I did, and then you launched Amos from right away from SPSS, your data will automatically be available over here like this. These are your variables, okay? It will be automatic here. But if you did not open Amos from SPSS and you open Amos right away, then you have to come to this and then select data so that you can navigate to select the data from where it is located. Hello, Christiana. Christiana Saka, you can speak to us.
Please, you were saying something, you were trying to show us how to identify outliers when my network went off. Please, can you show it? Because I didn't see it.
Okay. So I was saying that in the output analysis properties, okay, from the output tab like this, okay, there is an option where the software will demonstrate, will give you results on the test for normality and then outliers. So if you want to do that as part of the output, you should check it, and we checked it. All right. Your hand is still up. Are you okay?
Yes, I'm okay. Thank you very much.
You're welcome. Okay. So a quick check to see if you have the right data in Amos. Just click on this list variables in data sets. And I have this, and you'll agree with me, this is the data we have been working with. And I was saying, assuming you click on it and it comes empty, then it means you have to come here. You click on this, and then you go and look for where you saved your data. Okay. So file name will open a dialog where you go and locate where your data is, and then you pick it. Okay. But for me, I already have it, and my sample is 128. And it shows that there are no missing values. 128 out of 128 are all available for me. So, okay. All right. Now, what you see on the left-hand side here are the tools to work with. Okay. We have ellipse, rectangles, and then this wonderful tool here. If you place the cursor on each of them, it will put the name and what it's used for you to see. So the rectangles are used for drawing observable indicators or observed indicators or the measures. And then these are used for the unobserved measures. So let me just go back to here. So we say we use, these are ellipses, okay? We use them to draw unobserved latent factors or latent constructs. That is our construct that we have to define. It is not observed directly, but it is these indicators, which are properties that shows the existence of this construct, are what are being observed, and we use rectangles to represent them. So we are trying to draw something like this in the Amos interface. That's what we are trying to do. So we're using this and that. But this is a tool that helps you to draw a simple structure that combines this and that. So instead of drawing them one like this, you will use the simple tool that will help us do a shortcut. So when we pick it, you first click and drag and make your ellipse. Once your ellipse is established, you bring the tool and put on the ellipse. When it changes to red like this, then you click on it. It will create an indicator and this error term. I will explain this in detail once we are done with the first example. So our GEO has 5 indicators. So you have just created one. Let's create another one just by clicking. And 5. We have 5 indicators. So if you look at this, it is something similar to this. We have drawn the ellipse, and then we have our indicators. Now watch something. What we have here is like a regression that we have specified in a diagram form. These 5 squares are the observed indicators or the measurement items. They are measuring this latent construct, which we are going to be calling GEO, Green Entrepreneurial Orientation. Now, the extent to which this latent construct predicts or manifests in these observed indicators, the loadings will be recorded on these arrows. These arrows between the ellipse and then the rectangles. Now, so the assumption is that this latent factor is predicting these indicators. So, but this is not observable, but this is observable. So when we observe this from the field, it establishes a loading from these indicators to the parent construct. How much of this indicator that we have measured explains the latent construct, and then how much it doesn't explain the latent construct is reflected in the error here. That is these other arrows. So these are the error terms. We call these the error terms. Okay. Caleb, your video is on. If you can put it off. All right. So we have drawn for one. We need to draw 4 more of these. So let's go and do the second oval shape. And then we have, for SPP, we have 6 indicators. But remember in EFA, we dropped the 4th indicator. So which means we have 5 indicators. So we are going to draw 5 indicators for this one. 1, 2, 3, 4, 5. For the next one is MD, market dynamism. That one too has 4 indicators. Even to make life simple for you, just bring your variables here. Just by clicking this, it will list your variables for you. So GEO has 5, SPP has 6, but we dropped 4 in EFA. So we now have 5. So that's why I do 5. MD has 4, SMP has 4. So let's quickly do that. Now that we know how to do this, I'll just go straight away to draw the rest. So 1, 2, 3, 4. I could do the same and draw another 4, but there is a tool here that makes life simple. You can pick this tool. It's called the duplicate objects. If you select a highlight an object, you can duplicate it just by picking this tool to drag it. It works best when it is the only object you have drawn on the interface. If not, it becomes difficult to work with it. So since I didn't start by duplication, I'll just do the other one. 1, 2, 3, 4. Now, the next step is to label each of these diagrams or objects. We know the first one corresponds to GEO, and the second one corresponds to SPP. The third corresponds to MD, and the last corresponds to SMP. So if I pick the first indicator, GEO1, I'll just drop it here in this indicator. Now you realize that it is printing the labels for my indicator other than the label name. You can double click on it and come and remove the label name here. Okay, so that we are left with only the variable name. So you see, it's now left with only GEO1. But doing this in Amos is tedious. So how about we go to our data set and simply remove all the labels? So it's a common practice that usually once we have gone through descriptives and we are done, when we are left with the rest of the analysis, we normally remove the labels, especially for the variables we are going to use for EFA and then CFA. We normally remove them so that we can have just the variable names printed. So if I save this and I go back here, let me just save this and then close this and bring this back. We just have to close it and then start it again. But since we have saved, we can always come back to it. So let me just go to Amos. Okay. So now when we do this, it has removed all the variable names for the ones, the variable labels for the ones we are interested in using in this particular demonstration. So let's go ahead by populating it. So the next is GEO2 here, GEO3. You just click, drag, and drop. Make sure when you are dropping that object is highlighted before you drop. Now let's name the latent construct. You double click on it and then you can give the latent construct a name. So green entrepreneurial orientation. Remember, it's variable name, so it doesn't have to be very long. Okay, it doesn't have to be very long. Let me make it GRN or all right. Now you can put the full label here, but we don't want that because the space is too small to display the variable name. If I put the label here, it's a label that we printed instead of the name. Okay, so that is fine. Then we come to our second one here, SPP1, SPP2, SPP3. Remember, from EFA, we drop SPP4, so we will not include it at this higher level. You pick SPP5 and then SPP6. So here too we are done, but we need to label the latent, give the latent construct a name. Let me call this operational performance. So OPERF. All right. Then we move down to our third structure. We have MD1, MD2, MD3, MD4. Then we label the latent variable, which is market dynamism. We do for the last one, SMP2, SMP3, SMP4. Then we label this market performance. Okay.
It's supposed to be variable name, or it doesn't have an effect.
Oh, aha. So it's, yeah, thank you. It means you are following. It's supposed to be variable name. But you see what I was saying? If I try to put the full label here, market performance, it will display that one instead. Is the reason when we put the variable name here, it displayed it there. Okay. So, all right. Thank you for drawing my attention to that. Okay. Now we have labeled, for every structure, we have labeled almost every object except the error terms. You can label them one after the other manually, or you can let the software do it for you automatically. To do that, you come to the plugins and you come to name unobserved variables. All these error terms are unobserved, so you select that option and it will name them for you 1, 2, 3, all the way up to the last 18. Now we want to use the tools here to organize our structures we have made here, the objects we have made here, so that it will look nicer. Just like you can picture over here, we want to organize them this way, okay? So to do that, you pick what we call the preserve symmetry tool, and then you pick this, the rotate indicators of a latent variable tool. You can select these two together like this. When you come here and you click, it's, you see, it can rotate all the way like that. Not only is it able to allow you to rotate, it allows you, I think this is just for rotation, so let's do that. We have done the rotation, but they are not lining up the way we want it. You can also make the rotation this way. That is if you want the latent contrast to be on the right-hand side. This is also possible, okay? Now, look at this tool. This tool is used to reflect indicators of a latent variable. It is also useful. You see that GO1 has come bottom here. You may want it to go up here. And this particular tool can help you just reflect these to the right and to the left, just like that. And also help you to toggle between arrangement, the one being on top and the 5 being at the bottom. So these are tools you can actually play with. So you see, it flips them to the opposite side. It switches from the low bottom to the up, so that GO1 is on top and GO5 is at the bottom. Then I can now click on it to flip this back here, like a mirror, you see? So here, SPP1 is at the bottom and SPP6 is at the top. I can use it to flip it back here, click on it again. Now it arranges in order of magnitude, and then I can flip it back. So that is it. They are just tools to help you organize your diagrams here. Now I need to move them to so that they will align very well the way I want them to be. This is it looks like a car. It is for moving objects. So you click on it, and then you can come and move objects. All right. Now it is able to move all these objects together because we have selected the preserve symmetry. If that one wasn't there and I just pick the car to, it will just move only one object at a time, which we don't want. We want to preserve the symmetry. So we pick the two so that we can move objects like that. And by moving, you are able to arrange them to align well. And we can still use the same tool to spacing each object up. So with the same tool, if I click on the indicators, I can move the indicators back so that there is good spacing between the indicators and the arrows and all that. So you see, I can do the same here so that they will match. You can spread them out, you can bring them more together and all that with the same tool. So let me just keep them a little bit closer, but if you align here, so there's a lot of drawings, but it is better and it helps you appreciate how CFA is done in other softwares, because here you are able to do it with hand and you can appreciate what the software does. Okay. So now that we have done this, now they are nicely arrayed. Remember, as part of the validity, we're saying that even these constructs, they are related. They are related, they are correlated with each other. If not, there wouldn't even be a point to study them. So we need to also indicate that our latent factors are also correlated. And to do that, this is a covariance curve. It's a double-sided arrow to show that two things are related. We can do this manually by drawing a covariance curve to link all of these four latent constructs. So you pick that tool and you draw from GO to this, to the next, and to the next. So you have been able to link this latent construct to the remaining three. You have to do the same to this one. So since this is already related with this one, you only draw from there to here and from there to here. Now you've been able to link all these two to all other ones, but this one has to be linked to this. Okay. So if you look at each of them, 3 arrows should be attaching them, and that is nice. Now we drew this by our hand, and it's not aligning well like you expect them to be. It's not nicer this way. So you pick the hand tool here. It's like a magic wand attached to. I guess the women will appreciate this a lot. You touch and then you put them together like this, nicely for you. Nicely for you. Wow, like a magic wand. Okay. So this is one way. You draw it manually, and then you use the touch tool to arrange them, touch them up to look nicer. Alternatively, you can use the software to draw them automatically instead of using your hand to draw them. Because sometimes if you use your hand, you might miss linking some variables. So before you do that, you pick the single hand tool like this and click on your latent constructs. When they are highlighted blue like this, you come to plugins and you select draw covariances, and it will do it automatically for you. So that is cheaper and easier, faster, right? And to deselect all the highlighting, you use this hand tool. This other hand tool is for selecting everything, okay? Then you can use this for deselecting everything. All right. So this is our theoretical measurement model that we have specified. So we are telling the software that when you see GEO1 all the way to 5, they are measures of green entrepreneurial orientation, a latent construct. If you see SPP1 all the way to SPP6, they are measures of operational performance. If you see MD1 to MD4, they are measures of market dynamism. And that of SMP1 to 4 are measures of market performance. And we are expecting that these latent constructs are also correlated among themselves. Now, this is the structure you have drawn, and you are proposing this to the software. In the first instance, we didn't propose anything. We just selected only the observed indicators and gave to the software. And the software tried to classify them with component 1, component 2, component 3, component 4, which we know that it corresponds to these names. In CFA, as the name suggests, you are confirming. You now draw this structure specifying these relationships, and you are asking the software to compute the covariance matrix structure for the data and superimpose it on this structure to see the degree to which that covariance matrix structure fits or matches perfectly with this diagram you have drawn here. So in our evaluation, we'll be examining the degree of fit between this diagram and our data that we supplied. If the fit is good, it means the covariance structure of the data does not deviate from this measurement structure, and we are happy. If the fit is poor, it means this structure is not represented in the data set, and then we have problem. All right. So once we have drawn our structure like this and picked the variables from the data set to drop in the corresponding observed indicators, we are good to go to run our analysis. One other issue to go. You see that our variable labels cannot fit into the rectangles. We can easily fix this by coming to plugins and say resize observed variables. And the software automatically expand them just enough to capture the variable names. So at this point, we can even save and make sure. So now, once we get here, the next thing to do is to run calculate estimates. And this is the button you use. It has so as soon as you run, it gives you this additional tab. It makes it active for you. It said view the output path diagram. So you just click on it, and then it populates the estimates on your diagram for you. So it has, in regression, we have unstandardized estimates and then standardized estimates. You click on the standardized estimates, and it gives you the loadings similar to what you found in EFA. EFA came in a table. CFA comes in a diagram form, but it produces a table behind the scene which you can go and pick. Okay. So you will observe that they are similar, but they are different from what the loadings are similar, but different from what we saw in EFA. In literal sense, CFA is more stringent than EFA. So if your measures pass, the loadings are good enough in CFA, it tells you you have a good measurement model. Okay. So what judgment can you make from this? Apart from making judgment, passing judgment from the loadings, you need to first determine if the overall model fit indices. That is the fitness between the data set, the covariance matrix of the data set, and this structure we drew. The degree to which they fit is good enough. We need to come to the overall output. So you come to this object here, view text, and then it will produce a more detailed output about your diagram that you have produced here, your analysis here. So you come to the option model fit. There are a lot of things produced here, but first we want to check if the overall model is has a good fit. Okay, it has a good fit. So you come to model fit and you click on that, and then it gives you an expanded output here. Now, there are a number of things, parameters that have been produced here to help us make a judgment of the degree of fit between our supplied structure like this and the data set. There are a number of them that have been produced here to help you make a judgment whether your measurement model fits the data you obtain from the field. But we don't report all of them. As you can see, starting from what you see here, C main all the way down, there are plenty. So we are going to talk about the ones that are important for reporting. So the C mean you see here is chi-square minimization. Chi-square is used for comparing two things, okay, or two options, their score in on over one, something they share in common, over one variable. So here we have the structure as the common thing, and we proposed a theoretical structure, and we have the data. And what the software is trying to do is that it produces its own structure from the covariance matrix of the data and try to match that matrix with that structure with the physical drawings we did here to determine the degree to which they fit together. That is, if you overlap them, the degree to which they fit together or deviate from each other. So chi-square test looks at try to test the significance of the deviation or how different our drawing here is from the covariance structure of the data. To what extent is our structure that we drew here different from the covariance structure of the data we supplied it with? If it is significant, it means our structure doesn't fit the data. Our measurement model doesn't fit the data. If it is not significant, it means our measurement model fits the data. So it gives you what we call the chi-square statistic, which is reported here. C min, C for chi-square. So chi-square minimization statistics, 149.56. And then it gives you a degrees of freedom, and it gives you p-value. In statistics, we normally use the p-value to determine the significance of a hypothesis. So the default or the null hypothesis for chi-square test is that the covariance, the measurement model and the covariance metric structure of our data are significantly different from each other. They don't fit. They are significantly different. They are not significantly different. This is very confusing. They are not significantly different. They are the same. So if they are the same, that is the null. Then the alternate hypothesis for chi-square would be that they are not the same. The null, the default is that they are the same. They are not different from each other. And then the alternate hypothesis is that they are different from each other. So for the alternate, which is they are different from each other to be accepted, p-value should be significant. And for p-value to be significant, the score for p-value should be like 0.05. If p-value is less than or is greater than 0.05, then the alternate, which is the alternate hypothesis, which is the two are significantly different, will be discarded in favor of the null, which says the two are not different. So in this case, we have a p-value for the chi-square test, which gives us 0.104, which makes us to settle with the null hypothesis that our measurement model and the covariance metric structure of our data are not significantly different from each other. They are pretty much the same, which is the good news we want to hear. Now, the problem is that our sample here is only 128. When the sample size increases, chi-square test begins to be very sensitive. Chi-square test is very sensitive with respect to sample size. The higher the sample size, any chi-square test you do will be significant, showing that there is significant difference. Meanwhile, they might not necessarily be. Because the point is, when you have more data points, you can easily identify the minutest differences. But when the data points are not too many, you easily gloss over details and you easily see that they are closer than when the data points are too many. Okay. So when you are dealing with large samples, we use another criteria called the normed chi-square, where we divide the chi-square statistics by the degrees of freedom. This divided by that, and it gives you the normed chi-square. And ideally, you want this value to be less than 2. If you divide this by that, you want this value to be less than 2. If it is less than 2, regardless of the p-value, we will say that our measurement model fits well with the covariance structure of the data we supplied the software with. So you want this to be, ideally, you want this to be like less than 2. So here we have 1.1, which is good for us. But when it becomes difficult for us, we can accept up to values less than 3. Values less than 3 are also acceptable. We accept that because we are not basing our model fit decision only based on chi-square. There are other indicators you will pick from to make the conclusion. So just like you have a case in court and you need witnesses. The more witnesses you have telling us the same thing, the more likely you are to win the case, okay, or to defend yourself. So this is one of the parameters, that's the chi-square statistics. You want p-value to be less than to be greater than 0.5. If not, check the chi-square and non-chi-square. You want this to be less than 3. If you divide the chi-square value by the degrees of freedom, this one should be less than 3. So you will have to report the chi-square results. And then when it comes to baseline comparison, we are interested in what we call the TLI and then the CFI. These try to look at fitness between the measurement model and the data set by looking checking for model parsimony as well. Okay, it does a comparison between our structure and the covariance structure of the data set. And it tries to look at the degree of fit, which it computes from 0 to 1. 1 means perfect fit, and 0 means no fit, taking into consideration parsimony. So you want these scores to be as close to 1 as possible. So our rule of thumb, these are all other ones, but we normally focus on these two. The TLI, another name for the TLI is NNFI, non-normed fit indices. Okay, and this is comparative fit indices. You want these values to be closer to 1. The more they are close to 1, the better it is. I will check if I did not share that book with you, I will share with you. It's written by Hare et al. On multivariate data analysis, statistical analysis. It explains the theories and everything. If you want to know everything about these fit indices, it will explain everything to you. We won't have all the time to do all that here. So we will give you the books, and then if you want to make reference to why we report this and what they mean, they are all there. So fortunately for us, the rule of thumb is this should be like 0.9 and above, closer to 1. And ours is even more higher, closer to 1 than those ones. So you report TLI and CFI. Then the next thing of importance for us is RMZ. RMZ is root mean square error of approximation. And for our default model, the score is 0.035. What this does is the opposite of what TLI and CFI does. TLI and CFI tries to look at the degree to which, let me just demonstrate this on the office word for you to see. Maybe that one will help you understand all I'm trying to do here. Assuming this is the covariance structure of our data sets. And let me change the color of this. This is the covariance, this is the measurement model structure we drew. What the software tries to do is tries to overlay them and see the degree to which they fit together. So let me just do something small, since it will not fit perfectly. If they overlays them like this and they fit perfectly, this is absolute fit, complete fit. There is no difference. This is what we wanted, but we don't live in a perfect world. So you see that one of them will look like this. When you place on this, you see it is not fitting perfectly. Now, what TLI and CFI does is they concentrate on the region that it fits together to see out of 1, how the portion of the overlay that fits together and how much is it out of the whole. That's why we're saying the closer the fitting region is to 1, the better it is for us, okay? But what RMZ does, RMZ focuses on the degree of deviation. That it focuses on the unfitting aspect. It puts all the unfitting aspects together and report on that one. Whereas TLI and CFI focus only on the fitting side and compute it out of the whole, which is 1. So that we're getting like 90.97 something closer to 1. RMZ focuses on this part that is not fitting. That is root mean square error of approximation. It tries to look at the error margin here. It focuses on computing and reporting on the error margin here. And there are 2 ways of doing that. One of them is the RMZ, and that's what we have here. So you see that for a good RMZ, it should be approaching 0. What is it? It's here. So you see that that score is approaching 0. Whereas the baseline comparisons are approaching 1. That is, the fitting area should be approaching 1, and the non-fitting area should be approaching 0 to mean good fit. And that's what we have here. So the rule of thumb here is that a good RMZ should be less than 0.08. And we have 0.05, which tells us our model has at least a good fit, an acceptable fit. Okay, so you combine a number of these outputs to make a strong argument that your measurement structure, which is the green one here, fits the covariance structure of the data, which is the blue-black one beneath. So that is what we are trying to do in CFA. Okay. So I guess our time for, we are closing at 12:30. Okay, so we have more time. So let's continue and finish with this. Okay. So that is what CFA does. There is another measure similar to the RMZ, which also tries to estimate the degree of deviation, error error margin between the fits. In Amos, it doesn't produce, it's not produced automatically. You have to tell the software to produce that one after you have run the first analysis like this. So if you want to produce that second metric for the degree of deviation or error in the fitness between our measurement model and the covariance structure of the data, we go back to our drawing, and then we go to plug in, and we say, we select this option, standardized RMR. This is standardized root mean residual. Standardized root mean residual. So once you select it, it creates this small window for you. If you repeat running the analysis again, it will print the standardized root mean residual for you. And the interpretation is also similar to the RMC. This should also be approaching 0. And the same rule of thumb applies. A good one will be less than 0.08, and we have 0.06. So we now have, from multiple points of view, we now have evidence enough to conclude on whether our measurement model has a good fit, an acceptable fit. And yes, this is less than 3, and p-value is less than is greater than 0.05. TLI and CFI are all above 0.9, which is good. And then RMZ is less than 0.08, which is also good. And our SRMR, which we just calculated from here. Let me see if I'll find it. Okay, let me run it again. You see, where are you? Okay, which is also 0.063. So together, this shows a good fit between our measurement model and the covariance structure of the data. All right. So now that we have been able to determine a good fit for our data, our measurement model, we can go through all the other sundry reports that have been given to see which of them will be interesting for us. So analysis summary will just tell you how long it took them to analyze it for you, at what time. You don't need to report any of those. Sorry. Variable summary just gives us, summarize the variables, and we know this already. Okay. We know this already. These are the observed variables. And then these are exogenous unobserved variables, that's the error terms and all that. It just gives you a summary of it. We are not interested in that. Let's go to sample moments. Okay. We see some eigenvalues computed here. And you can see that for the first eigenvalue is for the first component, and look at the size, 14.45. Let's go to SPSS and check what we found there for eigenvalue. For the first one, so I computed, it was 6.20 for the first component. It does different things. Whilst the other one uses correlation, this one uses covariance metric structure to do that. So they are not comparable beyond the loadings of the indicators. They are not that comparable. So you even go to the loading and see that they are different. But we do this at the confirmatory level because it is superior to EFA in terms of placing how strict it is in computing the factors. It uses the rawest form of the information, which is the covariance matrix. Okay. Whereas EFA uses correlation, which is a more refined matrix. All right. So it just gives you some other descriptives, sample means, and all those things. about each of the variables, which we are not interested in. But if, for instance, you are interested in, you go and then inspect them. So these are some of the many outputs we don't necessarily need in our study. It gives you this correlation matrix similar to the ones we saw in the slides. So you see that all that correspond to the same component, they seem to have higher correlations, okay, coefficients. Then when it comes to MD4 to 1, they seem to have higher correlations, okay? And then SP1 to 6, they are also here. Their correlations are relatively higher among themselves than when you compare to their correlation with other variables. So that is it. Notes for the model gives you some summaries about the model fit, okay? Number of distinct samples of moments, 189. Number of distinct parameters to be estimated, 60. Degrees of freedom, that's the difference between the two, 129. It gives you the chi-square degrees of freedom, and then so, but this part, estimates, this is a very useful output. When you go to the diagram, it gives you the estimates, but it is difficult to report, sometimes difficult to report this in your work. You can report this in appendix, but if you want to report a table that looks like what we found in SPSS, I mean this, the rotated matrix here, if you want to report something that looks like this, you come to the text output and you come to estimates. Then it gives you standardized regression weights. This is comparable to what we saw in EFA. In EFA, it will put the construct labels here. That is the components 1 up to 4, and then it will shift them. But you can just put estimates here and list them like this. Already you know that these first 5 belongs to one construct, and it has given you the construct name, Green Entrepreneurial Orientation. It has given you the loadings. And the same principle, you want loadings like that are like 0.7 and above, ideally, but 0.6 are sometimes accepted, okay? Extremely low ones, you want to drop them. So SP1 to SP6 are also for operational performance, and we can see the loadings, okay? And then MD1 to MD4 are for market dynamics, and we can see the loadings as well. And then SMP1 to 4 for market performance, you can see the loadings. So how it arranges it here is a bit different from how EFA does it, but it's essentially the same. In EFA, we are assuming you don't know the components. So we list them and we disintegrate them. But in EFA, CFA, it lists all the estimates like this and assign them to their respective components, yes, which is even simpler and easier to report than CFA. This one will take a less space than EFA. So we normally will report this table in addition to other computations we make. So for CFA, because of the complex nature, Achu?
Yes, please. I just want to find out. You are talking about us reporting the standard regression weights. Of all the plenty things we do, is that the only thing we are going to report, or this is just one of them? Because the drawings, the arrows, and everything.
Exactly.
What are we going to report? Because it looks very plenty in our
It looks plenty.
Yes, yeah.
That's true. So I want us to use the remaining minutes to report, because of the complex nature of the CFA, to do the reporting so that you see how it is done, okay? The CFA table.
I didn't get that. I didn't get that.
I'm saying I want us to use the remaining time to report the CFA results.
Okay, all right.
Okay.
That will be great.
Yes. So I'll just showing you. These are the standard regression weights, and we are saying that since over here we are checking hypothesis also with respect to the degree to which our measurement model fits with the data, we need to also report the significance of each of these estimates. And these are provided here. The critical ratio we checked in the output, it is called the t-value. And its significance are produced here. What Amos will do is that any significance of less than 0.001, it will use 3 stars. Those, that is making room for 0.1% margin of error. We'll talk about that later when we are doing the actual regression. But if you see the stars, it just tells you that the p-value is less than 0.05, even higher than that. So we are going to report something from this table, this side, okay? Just the critical ratio, and then the estimates. And then we will summarize the information we need from the model fit indices, and then we are good to go. So in this text output, you can simply copy. The reason why it is not necessary to report both the diagram and this is that this information that you see here, it is the same information on the diagram. Let me just show that to you. So you see, but in the text, it is expanded for you to have more decimal places. Look at it, 0.73, 0.87, 0.87, 0.865, 0.86, 0.871, 0.87. So it's the same information here, okay? But this, we prefer this one. So like I was saying, even if you want to report this, or you can take this one to the appendix. Okay, so let me report this. You can simply select the table like this and copy. Since we are going to merge it with information from the table in the app, I'll open Excel and then put this one there. All right, so if I paste in Excel, it's already in a table, okay? So I can copy the second table to and then come and paste in Excel. And you just have to cross-check to make sure that they match perfectly. The information here, especially the indicators, they match perfectly. So once they match perfectly, from this side of the table, I can remove all the information we don't need. We only need a critical ratio. I can remove all these. And then, no, I think I made them, the labels shifted, so you just shift them right. Let me show you. Okay, the labels have shifted. The estimates are supposed to be here. So be mindful of that when you copy. So I just have to shift the whole thing so that it will be under the appropriate headers. Okay, that's good. Okay. I delete. I don't need the p-value because a critical ratio, I'll show you how it is computed. Let's come back to this side. The estimate, the raw estimate divided by its standard error will give us the critical ratio. And any critical ratio that is 2 and above is significant, whether you like it or not. That is the rule of thumb in statistics. Any critical ratio that is at least 2 and above is significant. So once I just want to demonstrate the significance of the loadings, I don't need the p-value, which is even printed in stars here for me, so I can remove them. So I only need this column from this table to add to the other table. Okay, so I can actually move this one closer. So another name for the critical ratio that we are all familiar with is the t-value. You come across it in regression, so let me use the t-value. It's the same thing. Now you see that there is no critical ratio for 1, GO1. When it comes to SPP2, there is no critical ratio for it. Let me explain the reason. You see that when it comes to the estimates, GO1 is fixed to 1, SPP1 is also fixed to 1, and MD1 also fixed to 1, and then SMP1 is also fixed to 1. Let me explain the reason to you. Let's go back to the diagram. Before we run analysis, this is what we drew. And you see that the arrow pointing to SPP1, GO1, and MD1, and SMP1 is fixed to 1. The reason we do that is that we fix the regression to be perfect. We assume it is perfect between the indicator, one of the indicators, and then the latest construct. When we do that, we give the software a reference point to calculate the critical ratios or the regression points of the remaining ones in reference to 1. We only use this to fix that it should calculate all the regression coefficients, the maximum to be 1. If not, it will give us haphazard loadings, and even the software will not even work. It is programmed to understand things that way. So you have to pick one of the, when you perform the structure like this, you have to pick one of the indicators and fix its path to 1. It becomes a reference point so that all regression estimates can be computed in relative terms under 1. If not, you will get some of them going above 1, like you see in the unstandardized. But because we fixed those ones, the standardized estimate cannot go above 1. Okay, so it is one of the requirements. In Amos, it does it for you automatically. Once you draw the structure like this, it will pick the first one and automatically assign it as a fixed one. All right. And it doesn't detract anything. So in that case, for each t value, we just, if the loading is not significant, then it won't even be 0.7. It won't be up to 0.7. It might be like 0.3, 0.2 thereabout. So it is a reason we ignore. So in reporting, you just type there fixed. You tell the reader that that was fixed. Its regression width was fixed. So we cannot compute the t value for it. That's all we do. Now we can simplify this side of the table even further. Instead of having these columns and arrows, we can remove them by just indicating, adding a row, inserting a row on top and say, the following indicators are green and entrepreneurial orientation. By doing this, we don't necessarily need these arrows and this other second column. We come here, we insert another row up, and then we put the name operational performance. So that from this line onwards up to here, that is indicators for operational performance. We just want to simplify the table. So just by rearranging stuff. From this type term onwards, we have market dynamism. And then from this point onwards, we are going to have market performance to market performance. So once we have done this, we can conveniently remove these two columns. That doesn't add much information to the table. So the table becomes like this. But we are not done. There are other computations we can do that will help us further make a judgment about the validity of our results. CFA also has a way you can compute what we call composite reliability. Composite reliability, so we represent it with CR. It is similar to the Cronbach alpha. So you can actually compare the critical, the composite reliability score for each of the set of measures, the constructs, okay, to the Cronbach alpha, okay. And then there's what we call average variance extracted, AVE. What it tries to do is that it tries to compute some sort of what you term as R square. The internal correlations here, it will square them and produce what we call the variance. When you square correlations, you get the squared correlation is shared variance. So when you have a correlation coefficient and you square it, you obtain what we call shared variance. It is similar to what we normally call the R square. It is called it's a form of coefficient of determination that is showing the strength of or the percentage of variance between the variables that is explained. Okay, so remember that all these measures, GO1 to 5, are trying to capture the notion of green entrepreneurial orientation. Now, when we square the variance between these set of measures and its latent constructs, we obtain what we call average variance. So we need to compute that. Averagely, how much variance in green entrepreneurial orientation is this set of measures able to account for? Okay, when we take the total variance, which is assumed to be 1, what percentage of it is given by, is contributed by, or is explained by these set of measures? That is what we call the average variance extracted. We need that to also make a judgment on the validity of our data. Then there are formulas. Achu, yeah.
Yeah. So you are mentioning what we will need and then the explanations to those things that we will need.
Yes.
So my question is, when do we bring them in? That's my first question. And then the other one has to do with the exploratory factor analysis and then the confirmatory one. Is it necessary to do the two in one study? And or you have to do one? If you are supposed to do one, which one are you expected to do? And at what time are you supposed to do the two, even if there is? Yes.
All right. Thank you for your question.
There is plenty.
It's plenty.
So we are, the head is getting way. So
I understand. I understand.
We can know our shortcuts.
Okay. So for the purpose of thesis, okay. Let me start from your first question. What I'm reporting here, I'm showing you the relevant things to report. 1, the loadings, the estimates. 2, the T values. 3, composite reliability, which is also a measure of reliability compared to the comparable to the Cronbach alpha we did, and average variance extracted. But these two are not automatically produced in any SEM output or in any CFA output. You have to manually compute this from the information you have here, the estimates.
Okay, so you mentioned it's not automatically produced in any SEM. So basically what we are doing is equal to SEM, right?
The SEM is the general name. The CFA is the first step in SEM, structural equation modeling.
Yes.
It is the first step. And what I'm saying is that all the SEM platforms, the softwares that we use for doing the CFA and SEM itself, it will not compute these two criteria for you automatically, but we can pick the estimates as the input into a formula to compute them.
Okay.
You get it? So I'm trying to present a table that you usually have to present after the CFA. So once we present this table, we only put the fit indices we explored earlier, the relevant ones. I will list them here and then put their values there. Once you have this table and the model fit indices, you have adequate information to report. That's all. So I'm trying to format the table, help us calculate the values for CR and AVE, and then I will have my complete table and information to show you what you need to report from CFA. And for your other questions, I explained initially that usually when you have come out with indicators that are pretty much new or involve new indicators that have not been validated before, then EFA becomes critical. In fact, there are some certain research studies that are just focused on developing and testing measures for new phenomena. Okay. For instance, somebody comes out with a concept like institutional void, assuming that is the first time we are hearing institutional void. Then the question is, how do we even operationalize institutional void? By operationalization, the question is, how do we even measure institutional void? Then that person being the first studying the concept of institutional void will define institutional void from his understanding of all the related terms like institutions, culture, and values and stuff like that to come out with what he means by institutional void. Then, based on the definition, he come out with indicators, plausible indicators. He will consult seasoned researchers and all that to help him refine the measures. Then he go and collect data to test the measures. Now he has collected the data. It becomes very imperative for him to do the EFA, which we did. After doing the EFA, he can go and collect another data again or use the same data to proceed to CFA. Because in EFA, you are only exploring. You are not telling the software to note that these set of measures are for green entrepreneurial orientation and these set are for operational performance. You just give these measures to the software, and the software, based on the scoring of these, will classify them into certain groups, and you now put labels on those groups the software does for you. Now, the second step is that you need to confirm what you obtain in EFA by taking it to CFA, where you now tell the software that I have this structure in mind. Try to fit it to the data and tell me the degree of fit. And then it produces this for you. So that is why the first one is exploring. And it becomes very necessary to explore when you have new set of measures that have not been used and been established. Their validity has not been established before. Then it becomes absolutely necessary for you to use the EFA. But assuming the measures we are using here, they have already been widely used and accepted, and their validity has been established, then the only must-do thing becomes the CFA, just to confirm in our study, okay?
Okay.
But for the purpose of thesis, it is not just doing what is important, but it is also a demonstration of your knowledge and understanding of the things you have studied. So regardless of whether they are existing measures or you are just develop them, we want you to do both EFA and CFA for thesis sake. In articles, yes, in articles, you only do what is necessary.
I was coming to say that then from your detailed explanation, you only get to do exploratory factor analysis when we possibly develop questionnaires ourselves or something. But if you're able to get measures from past studies that they've done and have done exploratory
validation
and have validated it, then we can move that one from there to the confirmatory rather than doing the two.
Exactly.
Your final statement sum it up that whatever it is, we need to demonstrate what we've learned. So it means we have to do the two.
Yes, for purpose of thesis, I mean like academic, when as a student you conduct thesis, you want to demonstrate broad knowledge in everything you are doing. So you report both.
Wow.
I hope you understand.
Yes, please. Thank you very much.
You're welcome. Okay. So there's
please, sir.
Hello,
Can I
yeah.
ask a question?
Ask, please.
So does it mean what we are doing, the purpose is for the thesis we will write later on?
And beyond. Yes, because see, what we are learning, you can use it to do research in your own organization or wherever, where you now, in that case, you focus on only the essentials, okay? But we give you everything so that you can also meet the requirement for your thesis. Is that okay?
All right.
But its application goes beyond. You see all the details we are reporting. When you are doing it for your personal or your organization level, they don't need all those details. But if somebody wants, to know to how rigorous your approach, the data collection and analysis is, then you should be able to demonstrate to them using these tools. For your organization, they wouldn't need these outputs, but you just want to do them and satisfy your conscience that, oh, my measures are pure. So I can go ahead and do my regression analysis and give them the report. All they want is the regression results, okay? But we are showing you a more systematic approach that will make your conclusion that you make at the end of the day bulletproof. That is why we are going through all this yama stuffs. Is that understood? We only have 5 minutes.
Thank you.
We only have 5 minutes to end. So I wouldn't want to start the calculation for this. It's just a table. I'll send the table to you. It's a template, an Excel template. Once you put these values in it, it will calculate the CR and the AVE for you. Okay? It will calculate that for you. So let me just let me just enter the model fit indices here for us, so that next time we'll just complete this aspect of the table, and then we'll go straight away to start with regression. Is that okay? All right. So
yes, sir.
Let me make some cells here and then just okay. Enter. So I come to model fit. This is where we are picking the model fit information. The first thing we want is chi-square. The chi-square statistic, and it's equal to 149.561. Degrees of freedom is equal to 129. And then we have p-value. P-value is equal to 0.104. And then we have the normed chi-square, which is chi-square divided by degrees of freedom, which is equal to 1.159. Let me be consistent. This is chi-square. It's a point. What is the point? Okay, all right. Then we come and report TLI and CFI. TLI is equal to 0.979, a good one there. CFI is equal to 0.982. And then we come and pick RMZ, root mean square error of approximation, RMZ, which is equal to 0.035. And then standardized root mean residual, SRMR, the one we found up there. That one was 0.063 something. Yeah. So these are the stuffs you normally report for the overall model fit. Okay. And we said for here, we want the chi-square value to be greater than 0.05. So check. Even if this is smaller, you want the normed chi-square, which is chi-square divided by the degree of freedom, to be less than 3. And we have 1 point something, which is very good. So it is another evidence that our model has a good fit with the data. And then TLI, Tekka-Lewis index, we expect it to be, what did I do? Merge. This is supposed to be a dot, not what we are seeing there. So let me just All right. Okay. It should be, these two should be closer to 1. And all of them are 0.9 and above. So we are happy. And this, that seeks to explain the degree of deviation or departure from fit. They should be closer to 0. And all of them are closer to 0. So we are happy. So you normally report what we call this, called the fit model, overall model fit indices. So you need to report on these, and then the table, the complete table, and then you put a small write-up. So when we meet next week, I'll complete the table, and then we will continue to try to make our regression estimates. Thank you so much for your patience.
Wow.
It shall be well, okay? So
I'll say, Papa.
I might just be better than you at this week.
It's too much.
Just have faith. Just have faith. You know, one thing is that some of you, your supervisors, will expect you to do the analysis yourself, whether you like it or not. But I said some of you.
I'll contact you.
Some supervisors.
I'll contact you.
Yeah, I don't do contracting. Others don't care. Others don't care if you let somebody analyze for you, but you must have the understanding of the output. You, the researcher, should be able to explain the output. You should be able to interpret it without making a mistake from that. Okay, so that is it for now. Have a wonderful afternoon, and we will meet, God willing, next week to try to complete our practical session.
So please, are you coming to Accra?
I said you people don't want face-to-face, so you will do it online. If you want face-to-face and you arrange, we will do. For us, that would have been better. You could make sure everybody has some kind of hands-on experience on this, okay? You could install the softwares for all of you and it sits on your computer, but you know, we appreciate the fact that the class is not just one class. You are some in Accra, some in Kumasi and all that. So since you are our customers, you do what you like. So
you'll hear from us.
All right, guys. So thank you so much. If there's no other question, enjoy your break, and then we'll meet next week to finalize the terms. So don't be. You will cross over. So can we continue using this same link next week? I don't know who created it, but can we do that so that we won't experience what we experienced yesterday? The same link. We will try and maintain it for next week's discussion. All right. Then au revoir.